Okay, so good morning, everyone. Let's start with the 27th edition of PADL, this conference on practical aspects of declarative languages in this sunny Denver. Sunny but very cold, unfortunately. So the chairs are Ezra Erdem and myself this year. And let me show you very quickly a few facts about the conference of this year edition. So this year we had 30 PC members from 13 different countries, and more or less one-third of them were women. And we also counted with the help of 10 additional sub-reviewers. As for the proceedings, this year we attracted 32 abstract submissions that eventually materialized only in 26 full or short papers, okay? From these 26 submissions, the PC members selected 14 full papers and 1 short paper, which are part of the proceedings, okay? And well, the program also includes a couple of invited talks by Annie Liu and Umutakar, Annie Liu that will start speaking right now in a few minutes. Thanks to them for accepting our invitation. We also have one extended abstract that was that is not part of the proceedings, is not in the proceedings, and a couple of lightning talks that will, these are short talks of 5 to 10 minutes that will take place. I think that it's today in the last session, at the end of the last session, okay? So if you like numbers, this is roughly the distribution of submitted and accepted papers this year per country. So USA is the clear winner, I guess, because, well, the conference is held here in the United States. And for the rest of the countries, the distribution is more or less similar. Well, perhaps Spain with a little more submissions. But, well, the clear winner is United States anyway. So this year, and this is already a tradition for PADL, we had an award for the best student paper. This year, the award went to Zachary Hansen for this paper, SM-based semantics for answer set programs containing conditional literals and arithmetic, by Zachary Hansen and his PhD advisor, okay? And since the competition was very close this year, we decided to add a second award, this honorable mention, to Kento Takyu and his advisor for this paper, enhancing a hierarchical graph rewriting language based on male-cat elimination, that will be presented in the first session after the invited talk. Okay. So congratulations to the two students that I guess are here.
Are you here, Zach and Kento?
Zach is here and Kento. Okay. So congratulations. And well, some miscellaneous information. The preliminary proceedings are available from the PADL webpage. They are almost identical to the final ones, but well, the actual proceedings will be available in the Springer's website in 1 or 2 weeks. And sorry for the delay, but this PDF is more or less the same. You can download the PDF. It's password protected, and the password is that Denver 2025. Okay. Let me know if you have problems with this file. So for presenters, please arrive at your sessions at least 10 minutes before the session and contact your session chair. Yesterday, there were several problems with some laptops. And, well, I mean, this is the usual stuff that typically happens. So please check your laptop and that everything was fine a few minutes before the session starts. And for everybody, you can also interact on Discord. POPL organization has set up a Discord forum, and there you can find an entry for each PADL paper, so you can ask questions offline or feedback or whatever, so it's an interesting opportunity. And finally, if you need a certificate of attendance, not an invoice of the registration, that's different stuff, but a certificate of attending the conference. I know that at least the Spanish people usually needs that. Perhaps people from some other countries, just drop me an email and I will send you the certificate. Okay? Well, I don't think I need to say this, but lunches are here, 4-square ballroom. We are here, so it's just 10 meters in this direction. Okay. Be careful because yesterday it was quite cold this place, so take some warm clothes with you for lunch. I mean, it's not in the open air, but anyway, it was a bit cold, at least for me. So thank you everyone that has contributed to the success of this conference. And without further ado, let's start with the first session. You want to add something? Or?
No, welcome everyone. So I hope you will have a personal meeting. Please ask questions and interact.
Thank you. Okay, so you want to start connecting the... You already have a microphone. Okay, yeah. Any Liu and a regular paper afterwards. Annie Liu is a professor of computer science at the Stony Brook University. She has worked on many different topics. In particular, she has worked on functional programming, but also on logic programming and distributed systems. It's not common to find a researcher that has touched so many different paradigms, and I think this is something that I find quite challenging and very inspiring. So she has made a number of significant contributions in these topics, in particular in program analysis and transformation, also verification, program verification, optimization of programs or algorithm optimization, and particularly incrementality, a topic that she's worked on for many years. So thanks again for kindly accepting our invitation, and please, the floor is yours. No, here is fine.
3, 4, 5, 6, 7, 8, 9, 10, 11.
Okay. Well, thank you for the talk. It was really interesting. So I'm familiar with the definitions of the Klingo semantics versus the DLV semantics, and even they... Oh, too bad. Well, even though they're both under the stable model semantics, they disagree on something like the company control problem, I think. So I'm curious because I've never really seen a good intuition behind what they're trying to... like.
So indeed, that he was asking just for stable semantics, because it does has the powerful constraint solving and the thing. They're different. This is just a small number that more cited, more known example. They give different meanings for the aggregation. I said half of those cannot do company control, half can do. Okay, and what's the assumptions? Even this, without aggregation, did they ever tell you the assumptions? They just said we're a closed word assumption, right? These people say we're a closed word assumption. Nobody ever defined them. So this assumption was defined. Actually, Michael Kiefer has really summary. I had this, but I didn't want to say. Their assumption was built into the procedure, built into the definition, like stable semantics, right? How do you do it? Ground everything, trial combination of variables. That's exponential. And for each of them, guess an answer. That's another exponential. And then for each of them, take the rules as some, delete some rules, delete some conditions. What reasoning logic does deleting rules and have and then after that, you do least fixed point. It's so procedural. Okay, so even Gaofang himself, right? He had one that says where's it go? I don't maybe I didn't put it here. Oh, here, Gaofang or somehow. Anyway, it meant two models for that tiny example, and later become one model. And so I went and asked him. He said, "Oh, I just made a mistake before." Right? Because it's even well-founded man. It's a procedure. I mean, it's called alternating fixed point. You infer all the truths, and you flip all the true and false, and you infer again. How in the world people can do that, right? So that's why they didn't even talk about the win-not-win example in those papers. They talk about P and Q examples. Win-not-win, you can't flip. But what I told you is just win, lose, and linear time. Okay? So indeed, if you want to figure out, and also because for some of them, because they do the semantics for aggregation, not the aggregation together with comparison. So they try to make some cases, anyway, even Mark Denneker had these things, has different fixed points for different, trying to match each of these things. Anyway, the point was they don't make the assumptions declarative. They make an assumption in their definition. Okay. This we just say, oh, what's the assumption reach predicate? For some of those, we have to say, for some predicates, they really meant certain. For some predicate, they meant something else. And in ancestor programming, if you're expert at programming ancestor programming, they sometimes add something called P if not the P, right? By definition, the stable semantic, they don't have a definition for not the P. And what they do in principle is not P becomes Q. So P if not the Q, Q if not the P, then they can allow P, Q to be both true or false. Otherwise, if you didn't say anything, suddenly P becomes false. So you have to do these hacks, and that's for the most trivial examples. Okay? And same thing with these others will also do some hacks. You can even think that virtual logic cannot do stable semantics. Oh, add a loop formula. Okay? But here you simply just say, gee, what's assumptions? And then I implement your assumptions in the best way I can. Okay?
Hello. Yeah, I'm curious about, do you still distinguish the classical negation and the...
Beautiful question.
Yeah.
Prolog, right? Called the negation is failure. Classical negation. Negation in our mind, kids, negation means negation. It doesn't mean 10 different things. Okay, so people ask me, no, negation meant exactly what I told you, the completion rule. That's just true and false. Negation of true is false. Negation of false is true. There's nothing else about negation. Okay? The assumption was just predicates whether it's complete or not. And right, negation means negation. If you meant when it's not, if is it false or is it undefined? Make that clear. That's all.
So we only keep one.
One negation. Yeah, one aggregation, one everything. That's agreement. Okay. Thank you for the question. Now remember, complete. Something to be not true directly, like you were saying, I'm a Stony faculty, and you are not a Stony faculty, that's fine. I infer true and false. And I can detect conflict if you did say you are fact and you are not. Absolutely. It's just as you think negation. Get rid of the those whatever hallucinations and all that crazy stuff.
Actually, I have a question about that. You mentioned the advantage of the unified semantics for combining logic system with an LLM. Can you elaborate on that? What is
I don't know. Do I have time? If I find out one slide? No, we passed time, right? Somebody, is there next talk coming or something?
Yeah, it's short answer.
Well, you have to know all of that. I have one slide telling you 6 ways, but it's like 2 times 3 ways to use LLM versus this, what I call all the rest we have called the rigorous reasoning, okay? And how do you get both together to get you the right thing? So short answer is you have to combine them absolutely correctly, okay? I don't have, I said I take a couple minutes to talk about it. I don't know, I thought.
Well, we can discuss that offline.
Yeah, anybody interested, I can show you the slides. I think they posted the slides too. If you want to see, I see if I can find it fast. One slide showing you all the ways to use all of them. Okay, so just a second. This is the, let's see, going here, here's my talks, with the one called
I
the,
think that the practical implications are.
yeah, well, just because they're assurance, but this is it. Okay, one slide showing all uses of it. Oh, that's the efficient implementation part. Here is it. Okay, that's final part. Before it's the same, and now the final part. And the only thing you really have to understand, LLM, okay, oopsie, doesn't give you any assurance, it's statistical, and this is what we have is rigorous. Okay, and what I propose the combination, I call the rigorous language model, which means you need to have that. And this is one slide showing you all the ways, each one is most famous now, popular names, to combine them. Okay, and mine was proposing the last one. You best use LLM to get you. Okay, this is pure LLM, just call LLM. This is a famous thing called a RAG. Okay, that's the example I gave you. Right? Ask what's the total of a sum of a list of expenses, like my travel to here. LLM will give you something. Now they try to even list expense. But LLM cannot do addition correctly. Okay, they cannot even do 1 + 1 = 2 directly. But most often it does it correctly. So what is the RAG, retrieval augment generation, saying, okay, I cannot do addition correctly, but can recognize you're doing addition, so let me call adder. Okay, so that's called the call. And then if I cannot even find the adder, the programmer giving new jobs, I call the LLM a program. This is the AI coding assistance, all those things. Okay, just use LLM to write the program to do it. Okay, but then here's our side, rigorous reasoning. Okay, pure, that's what we've been doing forever, all the logic programming, pure rigorous reasoning. But also, even for this, we need heuristics. It's answer programming, constraint programming, exponential. And how do you efficiently? You call LMs to find the heuristics. You don't call them for anything else. This is, I use this example just came out later, but the whole AlphaGo of fold that just got the Nobel Prize, that's exactly, they have to follow rigorous rules, but they, Go in particular, AlphaGo, absolutely Go of, the rule of Go, but use for heuristic. And the very last thing was I proposed was you have rigorous semantics, I call the spec. This is writing code, this is writing spec. The spec are the rules, okay? And you use LLM to build them, okay? And well, this was actually, I have a whole talk on this, but the idea is you use LLMs and parser, and you translate back to natural language, because I know exactly the semantics, and I even know 10 different ways of saying it. I can try each way to match your English, okay? And then, anyway, and the worst case, I cannot match any of them, I can go back, like a smart people, right? If I ask you a question, you do not know the answer. You don't just guess, hallucinate. You said, is this what you meant? Okay? Anyway, I said I have a whole talk on this thing, and the proposal on this thing. Okay?
Okay, thank you very much. Thanks again, the speaker.
Mark this? Okay.
Okay, the next talk is enhancing a hierarchical graph and writing language based on Merkab elimination, and the speaker is Kento Taki.
Hello, I'm Kent Taku. Thank you for the introduction. The main topic of our work is hierarchical graph rewriting. Hierarchical graph rewriting is an expressive formalism that subsumes many other formalisms, including term rewriting, process calculus, and so on. However, designing a practical high-level declarative language based on hierarchical graph rewriting is still a challenge. In particular, the right construct for graph cloning and deletion is highly non-trivial. In this work, we propose the graph cloning and deletion constructs for Elemental, which is a concrete programming language for hierarchical graph rewriting. Our design is based on MELL proofnets, which is hierarchical graph rewriting independently developed for linear logic. Hierarchical graphs support two structuring mechanisms, connectivity and hierarchy. For example, in organizational chart, connectivity represents who manage which group, and hierarchy represents the grouping of member and the nesting of groups. Connectivity and hierarchy can be found also in system configuration diagram and data structure. When we abstract these structures, all structures can be considered with graph structure with possibly with box structure. Hierarchical graphs are graphs with boxes, and it can represent all these structures. Elemental is a hierarchical graph rewriting language inspired by concurrent logic languages and constraint handling rules. In Elemental, graph nodes are represented as atomic formulas, and links are represented as zero assignment logical variables. Our implementation of Elemental comes with a parallel model checker with state space visualizer. MELL proof nets are a graph representation of MELL proofs. And MELL stands for multiplicative exponential linear logic, which is a practical sublogic for linear logic. In MELL cut termination, in MELL proof nets, cut termination is expressed as hierarchical graph rewriting rules, and some rules clone or delete hierarchical graphs. Here is an example of cut termination rules. This rule for MEL secant calculus is translated into this hierarchical graph rewriting rules, which clones the box structures. So, cut termination of MEL proof nets could be provide a useful design. Our main contribution is threefold. Firstly, we extended Elemental with process context aggregates and designed and implemented the MELL API for graph cloning and deletion constructs. Secondly, we showed that MEL proof nets and their cut termination rules can be directly encoded into Elemental. Thirdly, we encoded several process calculi and demonstrated the generality of Elemental with the proposed constructs. Now I move on to the explanation of Elemental. There are two approaches to definition of hierarchical graph rewriting. One is a traditional algebraic approach, which views pushout in category theory. The other is a programming language style approach, which is defined with abstract syntax and small step semantics. A comparison of hierarchical graph rewriting system is as shown in this table. Most systems are proposed as models. In contrast, Elemental is a hierarchical graph rewriting language with PL style definition. I'll explain the syntax of Elemental. The main construct of Elemental is named process with historical reason. A process allows null an atom with ordered links, parallel composition. A membrane which stands for box, or rule for subgraph rewriting. Graph with fixed ID nodes like these are often called pot graphs. Process template appears on both sides of subgraph rewriting rule. And process templates allow this hierarchical graph structure and the wildcards, which use the pattern matching of subgraphs named process context. The argument of the process context specify what free link name may or must occur. The left side of the argument represents explicit free links, and the right side of the argument represents whether there can be other unspecified free links. In this presentation, figure is blue boxes show the elemental graph, which correspond to the elemental code below. In this left-hand figure, there are I, A, and B atoms inside the membrane, and 2 G atoms outside the membrane, each connected by links of the same name written in capital letters. A link name occurring once, like this B, named is called a free link, which remain unconnected. Free links played key roles in subgraph matching and rewriting. Some atoms like A and B are drawn as arrowheads. The arrowhead indicates the order of links. This figure in the middle is a subgraph rewriting rule. In this rule, the P is represented a wildcard that has one link connected to the I atom, and the unspecified number of links going out on the membrane, which are described star Z, star X. This left elemental graph is written to this elemental graph to the right side by this rule. So this therapy matches these A and B atoms. So the membrane is paired off, and the I atom is written to N atom. In hierarchical graph rewriting, we often want to clone subgraphs. Cloning of subgraph is a highly expected feature of high-level graph rewriting language. But to handling edges is not obvious. For example, we want to clone this subgraphs with B atoms. In elemental, which handles port graphs, the reality of A and C cannot be changed. We must somehow splice two clones of the subgraph into the context of the original subgraph. In original elemental, the API named NLMem for nonlinear membranes provides subgraph cloning constructs. The details are omitted, but this figure shows how a copy token clone this membrane with therapy. However, we want to give a mathematical or logical background to this design. The design of graph cloning construct is highly non-trivial, even in algebraic approaches. A comparison of graph rewriting system with cloning constructs is shown in this table. Most frameworks adopt approaches based on category theory and description logic. However, we propose an approach that aligns with PL standard definition. At the same time, we want to incorporate a mathematical or logical background. So our research question is, can we justify our language design based on some mathematical or logical system or design guideline? Now I move on to the explanation of MEL proofnets. Firstly, the definition of MEL formulas are as follows. The formulas allowed atomic formulas is negation, tensor, per, bang, and question. Tensor and per are called multiplicative, and bang and question are called exponential. Negation appears only in atomic formulas in the basic syntax. And otherwise, it moves or removed by the Morgan duality. Next, linear implication is defined by these formulas, and classical implication can be translated by using linear implication and ban. This figure shows the inference rule of MAL sequence. The definition is standard, so we omit it. But I'd like to point out that this promotion rule is important. It is known that the cut emission theorem holds for MELL. MELL proofnets are graph representation of proofnets, proofs of MEL sequence with higher level of abstraction. For example, both left side and right side proof tree can be translated into the same proofnet. MEL proofnets are defined in 2 steps. The first step is the definition of graph structure named proof structures. The second step is the definition of geometric constraints on proof structure using switching graphs. Firstly, an MEL proof structure is a directed acyclic merge graph that combines the cells and wires and the promotion box. This promotion box corresponds to this promotion rule for sequence calculus. Next, MEL proofnets are defined by proof structure and switching. Please refer to the paper for detail. For example, this proof tree can be represented as this proofnet. The cut emission rule for MEL proofnets are hierarchical graph rewriting. Hierarchical graph rewriting rules corresponding to those for MEL sequence calculus. For example, this ban rule of MEL sequence calculus can be translated into this hierarchical graph rewriting rule. By using this rule, this left promotion box is moved into this right promotion box. Next, this is a ban contraction rule for MEL sequence calculus. This rule can be translated into this hierarchical graph rewriting rule. This rule involves a box cloning. This figure shows the simplification through multiple steps of cut elimination. This bottom left proofnet simplified to this bottom right proofnet. For MEL proofnet, the following properties holds cut elimination theorem, stability, confluence, and strong normalization. Now I move on to the design and implementation of the MEL API. We wish to establish a closer connection between Elemental and MEL proofnets by providing Elemental with well-motivated graph cloning and duration constructs inspired by MEL proofnet. Firstly, we define a new syntactic construct, process context aggregates. This construct represents a multiple copy of NI-P as process context. This number of copies is determined by the number of links represented by these bundles. So we can now represent an unspecified number of wildcards. Next, I'll explain the design and implementation of the API. We can describe clone and duration using process context aggregates. For instance, the API named MELL copy clones this membrane with free links. The specification of MEL copy can be written in this graph structure. It is necessary to ensure the consistency of free links before and after cloning. This $A, $B, C1, and C2 are arguments introduced to ensure the consistency of free links. Firstly, I explain this X. When $P is cloned, X is also cloned. But to avoid the increasing free links, $P is with 2 port is are generated and each connected to cloned X and C1 or C2. Next, I'll explain this star Z. Star Z is unspecified or number of free links. When the P is cloned, star Z are also cloned. So the number of free links is double. To ensure the total number of free links before and after cloning does not change. We can now specify this structure with 3 ports to connect cloned star Z to original star Z with process context. The process context aggregates are introduced to represent an unspecified number of $A. We implemented it as API of elemental runtime. Now I move on to the explanation of encoding. Firstly, we show that MEL proofnets and their termination rules can be directly encoded in elemental. By directly, I mean that each termination rule encoded into one elemental rule. The encoding step is as follows. Firstly, the encoding of cells and wires are shown in this figure. The non-commutativity of input of tensor cell and power cell is represented by atoms, while the commutativity of the argument of AX and cut is represented using membranes. A contraction cell with commutativity input and a single output is represented by using both an atom and a membrane. The encoding of promotion box is shown in this figure. The outer frame of the box is represented by a membrane, and question gamma is represented by a bundle. And the blank white space is represented by a process context. So the MEL proof structure can be represented by a combination of cells, wires, and boxes. Next, we show that all 6 termination rules of MEL proof nets can be directly encoded into elemental with the MEL API. We show the encoding of the following 3 rules in both non-trivial box operation as example. Firstly, we show the elemental encoding of Ban rule. The diagrammatic representation is shown in this figure, and textual representation is shown here. The only thing that has changed between the antecedent and consequent is the position of these braces. The migration of the box can be represented by the movement of the braces. Next, I've shown that elemental encoding of band contraction. The diagrammatic representation is shown in this figure, and textual representation is shown in this code. To encode this operation, 3 rules were necessary with NLMM API, but now it can be encoded with 1 rule using MEL copy API. Next, we constructed and visualized state space of termination. As an example, let's consider beta reduction of the simply typed lambda calculus. By the Curry-Howard isomorphism, the type derivation tree has a corresponding net, and its termination corresponds to beta reduction. In this example, there is only 1 reduction path of beta reduction, but we are interested in the state space of the termination of MEL proof nets, which corresponds to this beta reduction. This state space is constructed and visualized using elemental runtime with the MEL API. In this example, we can see many reduction paths of termination. Also, by observing this state space, we can confirm well-known properties such as Church-Rosser and strong normalization. And we also can confirm non-trivial properties such as the existence of redundant paths like this. Next, we try to add rules have been proposed in the literature, and we can readily observe changes in the state space. For example, this rule, which pushes the weakening node, is used in the expression of substitution. But if we make unrestricted use on this rule, conference is lost, as I show in the next slide. This space or the added rule in the previous slide is shown in this figure. The number of final states increasing to 4, so conference was lost. In conclusion, rules could be easily added, and consequence of rule addition could be visually confirmed. So, Elemental with the MEL API is useful as a workbench for proofnets. Next, we show that several process calculi can be encoded in Elemental. For example, we encoded replication rule of the ambient calculus, where ambient are box structures that may be duplicated, migrated, and deleted. The encoding of this open rule is this Elemental code. So, Elemental using MEL is sufficiently general for modeling and computation. Our related work is as follows. Please refer to the paper for detail. In conclusion, we introduce MEL API, which is based on the categorization rules or MEL proofnets, to perform cloning and deletion of hierarchical graphs in Elemental. So I hope that this work will be as a beneficial bridges to both sides. Thank you for listening.
Any question or comment? Well, in the meantime, I have not a conceptual question, but more a contextual question. I wonder if the contribution of your paper is more on the design of this language Elemental that is now more general and can do more things, or you think that your contribution can also be useful to the people that is working on mail-proof nets and can now use this language because it's better than the existing language to represent these proof nets?
Thank you for the question. I think that this contribution is in general useful for hierarchical graph writing.
So in other words, the resulting language, this elemental language extended to deal with these proof nets, is competitive with existing languages for proof nets?
Well,
If there are such languages, I don't know.
to the second session of PADL, which is a bit related to type checking and functional logic programming and so on. And the first talk is by Jim Newton about very long title. So can you switch it up? Can you switch? So now we can see. Okay, about type checking heterogeneous sequences in a simple embeddable type system.
Okay, thanks everyone for coming to listen to my talk. It's always a pleasure to talk about the things that you're interested in, especially to an agreeable and friendly audience. A quick overview of what we're going to talk about. I'll talk a little bit about the history of the project, and then rather than giving a lot of definitions and mathematical formulas, I want to go through a simple example, and I think that most of you can fill in the blanks and understand what it is that we're trying to do and what we're trying to represent. And then, as was explained in the paper, there are several very interesting corner cases and interesting challenges, technical challenges in the project, and I want to spend most of the time talking about those particular challenges. And there's some final thoughts. So a little bit of a history of the project. So when I started working on my PhD quite late in life, at the age of almost 50 years old, I presented a paper at the 2016 European Lisp conference about something completely disassociated from my PhD thesis, and then later on that involved into the thesis itself, and then I presented that in 2008. One of the comments from the committee was the thesis and the research was all about the type system in Common Lisp, and they asked, well, can't you generalize this to something more accessible to a general audience? And so what we're going to see today is some of my work on that, where I've extended this to the Scala, Clojure, Python, and then the original implementation is in Common Lisp. These are freely available for download from GitHub. So an example. What are regular type expressions, RTEs? I'll use the word RTE a lot without repeating potentially what it stands for. Basically, what we want to do is recognize patterns which have some type, recognize sequences which have some type of pattern in them, and where the patterns form something that looks like a regular language. So what is the pattern here? Here we have an integer followed by some numbers, which might be floats or doubles. The notation here is that F represents a float, and otherwise the floating point is a double. So integer, some floats, integer, some floats, etc. So I would like to define or declare some regular expression to declare that to describe that type. A regular expression looking something like this: integer concatenated with double or float, and then that occurring one or more times, and the suite occurring maybe 0 or more times. So there are a couple of challenges in there. The highlighting doesn't look so nice. But one is, how do we represent this as a surface syntax in lots of different programming languages? And the second challenge is, well, how do I even represent logical combinations of types in a language-independent way? So some languages will let me represent intersection of types, but I don't have any programming language other than Common Lisp which lets me represent the complement of a type. So I would like to have any Boolean combination of types, as well as several other types, types of types. So how is pattern recognition of sequences normally done? Well, what you would want to do typically is convert the expression into some sort of finite automaton. And then, well, there's immediately a challenge. How do I do that in different programming languages? That needs to be done at what I'm going to call compile time. So even though that might be inefficient in some sense, there may be some complexities there that we're not so happy about. At least that computation happens at compile time rather than at runtime. And then at runtime, we want to use the finite automaton to match the sequence, to decide is a given sequence a member of the language of that regular expression or the language of that finite automaton. So the way it basically works is given a sequence, 13, 2.0, 6.0, and so on. We start in the initial state. We see that 13 is of type integer, so we move to state 1. We see that 2.0 is of type double, so we move to state 2. We get another double and then an integer, a string, 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 integer, double, 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 integer, and then again double. And we're at the end of the sequence, and we end up in a state which is marked with a double circle, so it's an accepting state. So we know that the sequence does match the expression. If anything else happens, for example, if we ever encounter a type or an element whose type is not listed on the transitions coming from the state that we are currently residing, or if we reach the end of the sequence and we're not in a final state, then we reject. We say the sequence is not an element of the language of that regular expression. One thing that you might notice or might not notice is that the decision criteria is linear in the length of the sequence. So regardless of the complexity of the expression might be arbitrarily, hugely complicated syntactically, but to match a given sequence, we can do that in linear time by traversing the sequence exactly once. There's some problems that arise when you take an example that's not a trivial example. Suppose we're looking at this sequence, 2, 3, and then some floating point number. We see the first element is an integer, so we arrive in state 2, and then the next element is a 3, which is both an integer and a number. And integer is a subtype of number. So what do we do? So we might, for example, traverse the integer transition, and we find that the next character or the next element of the sequence is not of type string, so we backtrack. Now that's horrible because now the complexity of matching becomes exponential and no longer linear. So potentially that could work, we could get the right answer, but we really would like to avoid backtracking. So the solution that I propose is that we partition the types always into disjoint types. So 3 is an element of integer, but it's not an element of number and not integer. So then we can unambiguously, deterministically choose which transition to traverse, and we see that the sequence does match well, it is in the language of the finite automaton. That brings another challenge. Given a set of types, how do I partition the types? And what is a sufficient partition for the finite automaton to actually represent the language of the expression? And it wasn't at all clear to me at the beginning what is a sufficient partition. So here are the 4 challenges I would like to talk about in the remaining few minutes of the presentation. How do we represent these expressions in a way that can be translated into many different languages? How do we represent a type lattice in a language which doesn't already have a type lattice? So we can represent union, intersection, complements of types. How do we construct a finite automaton on this regular expression of types? Classical finite automaton theory talks a lot about languages on finite alphabets, but in this case, the set of objects in a programming language is an infinite alphabet. And then how do we make sure that those finite automaton are deterministic? So we have to do a sufficient type partitioning. So the first one turns out not to be so difficult. In the 4 languages that I've implemented in, we can represent in Scala with, I've defined a type hierarchy called, I forget the word in Scala used for this, ADT, algebraic data type, I think it's called, to be able to represent instances of this AST, algebraic syntax tree, or abstract syntax tree. So the internal nodes of the tree are the operators of the regular language, of the regular expression, and then the leaf levels are interfaces to the built-in types of the programming language, be that Python, Scala, whatever. And so here's the syntax in Scala. So we're using the infix operators which Scala provides and lets us override. In Python, it looks something like this. So we have constructors for the different objects, star, cat, etc. In Lisp, being homoiconic, we represent the abstract syntax tree just as an S expression in the language. There's no need for additional class definitions to be able to represent the expression tree. The second challenge then is how do we represent a type lattice in these languages? So I want to be able to reason about and or not of types, even if the language doesn't support them in a built-in way. We want to somehow wrap the type system or embed a new type system in the type system so that the regular type expressions can manipulate that embedded type system. We need to support a type lattice. It needs to be simple. So what is the simplest that it can be to represent the types of operations that we need to be able to do? As we'll see, there are two predicates that we have to implement in all the language. One is a membership predicate given an object is an element of a type, of a particular type, and that must be a Boolean. So it must answer true or false at runtime with no ambiguity. And then there's what I call a semi-Boolean predicate. So the subtype question is one type a subtype of another, can be answered yes, no, or don't know. So whenever the system doesn't know, it must answer don't know. When it answers true, it means I've proved this is not a subtype. Or when it answers true, I've proved this is a subtype. When it answers false, I've proved that this is not a subtype. So again, there's a similar type of abstract syntax tree that you can use to represent types, with the internal nodes being the Boolean operators. As I said before, the membership predicate is always answerable, so we know that -42 is a member of the integer type. We know that 7 is a member of the type, which is the union of string and integer. And we know that 36 is a member of the type odd p, which is defined by some user-defined predicate. More interesting, and what makes the project quite interesting, is that given a set of types, we don't always know the subtype relations between them. So is integer a subtype of number? Yes. Is string a subtype of integer? No. Is satisfies odd p a subtype of integer? So you and I know that all odd numbers are integers, but given that this is a user-defined type, the type system doesn't know that, so it must answer don't know. There are many other reasons why the subtype question is unanswerable, in particularly because classes are loadable at runtime in some languages. So there may not be, A and B may not have a subtype relation now, but maybe later there is some type which inherits both of them, or the type lattice can change at runtime. Okay, so now how about how do we construct these these finite automata from regular expressions? So classical finite automata theory defines something called the Brzezowski derivative. I'll talk about that in a little bit, but we had to actually adapt that to our work because there are some interesting theoretical mismatches that will, again, make the problem interesting. We want to construct a finite automaton like this from this regular expression, from this regular type expression. And so the finite automaton is going to have transitions labeled by types, and the types are going to be Boolean combinations of the types that you see in the given regular expression. The Brzezowski derivative is defined sort of as a pattern matching. There are these recursive rules, which, for example, for a R star, you find the derivative of R and then do something to that result. So there's these recursive rules where the derivative is called or is constructed on some subpart of the expression. And then there are the termination rules. So when we come to the empty set or to the language which just contains the empty sequence, then the derivative is the empty set. But the more interesting cases, which did not match Berzovsky's original definition, were the leaf level cases of the types. So when we descend the regular expression down to the leaf levels and we get types, we have to know, are we taking the derivative of some type with respect to some other type? We must know whether the types obey a subtype relation or whether the types are disjoint. With that definition, the regular expressions work correctly, except there's a problem. We don't always know the subtype relation. So how do we compute the Berzovsky derivative in a situation where we don't know what the subtype relation is? You could get a very different result if the types are in a subtype relation or not. And how do we sufficiently partition types so that this expression is always evaluatable? So basically how we construct the finite automaton is we somehow extract the types we're interested in from the expression, integer, string, etc. We perform this partitioning, which I'm going to call MDTD, maximal disjoint type decomposition. And then for each of those types, we compute a derivative with respect to that type of the original expression. So if we're partitioned into 10 types, we must compute this derivative 10 times, and then those types become the labels of the transitions. Let me show a more interesting one. When we have decomposed the types, when we have this type string and integer, we decompose them into string and even, string and even, string and not even, not string and even, not string and not even. So we have more or less 2 to the n different types in our partition. And then these types, if we follow the rules specified on the previous slide for the derivative definition, the derivative is calculatable. If we look at the state 3 here, we have 3 types that we have to consider. We partition that and we get potentially 8 different types. So we have like this 2 to the n relationship of the number of derivatives we must take at each step. But you notice string intersected with integer intersected with even is obviously empty. There's no object which is both string and integer. So many of the intersections will go away. They're called, I'm calling these unsatisfiable, a type which has no inhabited value. So if we can disjoin the types into a sufficient partitioning, then we can construct the finite automaton. But the question now is, how do we do the type decomposition in such a way that this expression is always computable by the recursive rules we saw, even in the case when the subtype relation is unknown? So imagine that we have a set of types that are partially overlapping. Some are subtypes of the others, some are disjoint. We want to find all of the non-empty intersections, and we want to somehow colorize the graph into all of the regions that don't overlap other regions. The way we do that is, well, let's take, rather than all of the 10 types here, 8 types here, let's just take 5 of them. So we start with the universe, which is called sigma in this case. We intersect with A1 and not A1. So those are clearly disjoint, and their union, again, is the universe. And then for the next step, we take the next type and intersect each of the leaves with both A2 and not A2. But what we see is that since A2 is a subtype of A1, then A1 intersect A2 is equal to A2, so this type name can simplify. But since A2 is a subtype of A1, then A1 intersect A1 not intersect A2 is empty. So some of the leaves get pruned very quickly in the process, so we avoid a super exponential explosion. The complexity is still exponential in the case if we have to actually compute exponentially many intersections, but many of the leaves get pruned very quickly. So we intersect with A2, not A2, A3, not A3, A4, not A4, A5, not A5, and in the end, because of the different disjoint relations and subtype relations, we get, I think it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 different types rather than 32 as you might expect in worst case. So these become the types we want to plug into the Brosovsky derivative. And so it turns out that, well, by construction, each of the types computed is either a subtype or disjoint type to all of the A1 through A5s, and we know which by construction. So even if the type predicate is not able to answer the question, is this type a subtype of some type or disjoint, we know by construction which one it is. Is it a subtype or is it disjoint? We know that all of the computed types are mutually disjoint by construction again, and we know that it is a partition of the original space, which is the universe. So these turn out to be the exact properties we need to compute the derivative. So how does that help in assuring that the finite automaton is correct at runtime, that we do get the correct result? So rather than having integer and number as transitions, what we have is integer and number, integer and not number, not integer and number, not integer and not number, except that some of these go away if the subtype relation or disjoint relation is known. But if we look at int and odd, we don't know anything about the subtype or disjoint relation between those. So in that case, we do get potentially 4 transitions, integer and not odd, not integer and odd, even if the human being knows, for example, that not integer and odd is empty, for example. And that means that if we have a transition, for example, integer and not number, that transition can never be traversed. There's no object in the language which is both integer and simultaneously not a number. So this state 1 is useless. We don't have to actually generate it when we construct the state machine. And all of the states which 1 leads to can be omitted as well. However, in the case of a type such as string and odd, we know that that's unsatisfiable, but the machine doesn't. So we'll get transitions which exist in the state machine's construction at compile time, but at runtime, there's never going to be an object which satisfies that type, so the transitions will never get traversed. And in the case of int and odd, again, syntactically, it looks exactly the same as string and odd. However, this is actually a useful transition because whenever we get an odd integer, the transition would be applicable. So in some cases, we can't eliminate useless states. So minimizing these finite automata is then, well, it's impossible to completely minimize these. However, even in the case of useless transitions, the runtime check is still correct because whenever we get an object at runtime, we can test because the membership predicate always returns true or false. We can know if a particular object is a member of this type or a member of this type. Okay, so in conclusion, what we've done is we've come up with a way to efficiently pattern match or recognize patterns in what I call sequence of any, which this is the Scala syntax, and extended to several different programming languages. We've extended the Brosovsky derivative to accommodate types, and particularly types in a hierarchy where types may overlap or have subtype relations. We have a correct finite automata even in the case of an indeterminate subtype relation. Again, the code is available here. I invite anybody to take a look at that. say just a quick word about critical feedback, that in a peer review process, researchers depend on other people to find problems with their work, not to be, nice citizens, but to speak up and say, hey, there's a problem here, there's a problem here. So I completely welcome feedback, even if it's critical feedback. And with that, I thank you, and I'd be happy to answer any of your questions.
So, are there any questions? So maybe,
You mentioned I've never heard of any language where you can intersect the negation of an integer. And have you heard of Elixir? Okay, Elixir is a language in the family of Erlang. So basically, it's more or less on types. It's as a very simple type system like Prolog, but recently they have introduced a set-based type system where they also have intersection, union, and negation. So maybe some of your work can be used to give some sense, because it's a quite complicated type system, just to let you know. Okay.
So when you're doing these types, all of the types you have up here are like either what are built-in types in most languages, or user-defined types like odd, or user-defined predicates like odd. Can this system be extended to like composite types? So like if I had like a list of integers or something like that.
This simple embedded type system can encapsulate any type built into the language. So if the language has a composite type, it can be brought into the language trivially using this protocol. But some languages, such as Python or Clojure, don't have tuple types, for example. There's sequences, but not types of int or types of string, or sequences of int, sequences of string.
Kind of subsumed by sets and tuples, kind of subsumed the composite types we might want to bring into the language.
If you had a use case where that's not a sufficient generalization, I would like to know about it. But I didn't want anything in sets, the simple embedded type system, which was not supportable in all of the languages that I was trying to support. Yeah.
Hi, I wonder if there's been any research into what something like this might look like in a dependently typed setting. Or there's a concept of heterogeneous sequences, right? And I'm wondering if, what would happen if you said, well, I have a sequence that has types that satisfies this pattern, right? Where you could define your predicate at like the type level. Do you know of anything like that?
I know that Scala 3 has these dependent types, but I haven't not worked with them yet, so I don't know what the implications are of that. The membership predicate must be answerable. So in a dependent type system, given an object at runtime, can you know whether it's an element of a dependent type or not? With certainty? I don't know.
Oh, there it is. Hi, I just had kind of two comments. Following up on the discussion of type systems with negation, I thought I would just shout out, there is a pretty cool type system called cut out again, a language called ML from HKUST that has a whole kind of type system with proper negation. And also following on the dependently typed comment, there's also kind of an interesting line of work, I think, by Alan Jeffrey from a few years ago on linear temporal logic in a dependent type system, which I know sounds maybe a little unrelated, but does actually talk about sort of sequences and kind of non-trivial sequences of different types in a dependently typed setting. So I don't actually have a question. It was very interesting. I'd love to read more about this. I thought I'd just shout out two things that I like. I think the ML struct work, to my understanding, there's a variation on the notion of a constructor. So it's kind of not the same familiar thing you would think of as a constructor. Yeah. Yeah, so it's definitely a little bit more complex than that. Yeah.
So I think we have to stop the discussion and we can extend it in the coffee again for the presentation and the discussion. Haskell-based spreadsheets, and from Madrid, and Ignacio will present the paper.
And the Technical University of Madrid. The talk or the tool that I'm going to talk about, you can trace back the origin back to our final and degree project on the undergraduate at the university. This was some work with Luis, and Julio, who is here, was also a participant of that. And well, I'm going to talk about spreadsheets. I will assume that all of you know what a spreadsheet is. If you prefer to look at it this way, sorry. This is like a tabular representation of some computations that was used more than 3,000 years ago. And as every spreadsheet, it contains errors. The computational model of spreadsheets is very widespread. Microsoft Excel alone has close to 1 billion users. And with recent cloud-based spreadsheet software, there is estimated that more than 2 billion users use them every month. It is, as well as successful, it is very error-prone. And there are many horror stories that I recommend you to look for. There is, in fact, an European interest group on the risk of spreadsheets, and they have on their web page a collection of these horror stories. But the important thing is that spreadsheets are used by big companies to make decisions, and 94% of the spreadsheets contain errors. And in those spreadsheets, there's close to 5% of cells that are errors. To visualize this, you can here have a spreadsheet, and every cell that is colored in red is expected to have like an error. To visualize how many errors there are usually in a spreadsheet. So what are the solutions that they are proposing to work with this? Well, they recommend you to follow some development patterns and design patterns, and also to use some analysis tools. And lately, they try to predict what the user is trying to do in order to prevent the error. So we thought about this, and we started to think, why not using functional programming? At the end, spreadsheet software, in some sense, are a decorative, side effect-free computational model. And even maps and folds occur naturally. You start working with ranges to apply a transformation, you filter, you reduce the cells into one value. But the problem is that a spreadsheet lacks some of the functionalities of modern programming languages, especially type systems. And many of the errors that occur in spreadsheets are related to this kind of programming errors, the lack of a decent type system. There are dynamic values, casting of them, how to interpret blank or empty cells. You start to work with ranges that are not very delimited, and you apply functions to ranges that are not complete. And we know that type systems can help you to prevent some errors. We have seen how TypeScript, for example, has taken the JavaScript world into introducing a type system on the language. So we started with an hypothesis that maybe if we reconstruct the spreadsheet idea around a modern functional programming language that has a type system could improve, like how do we work with them. And if we start thinking about the spreadsheet as a real programming environment, we can start thinking also about how to introduce some of the techniques that we use, how to apply testing or advanced testing techniques like property-based testing, how do we debug our spreadsheet. And this is when we came up with Haskell. This is the tool that we propose, in which we want to introduce all of these features that modern programming languages have. But Haskell is not a substitution of the things that we have. It's not either an implementation of Haskell or how to interact with Haskell through an spreadsheet. The idea of the tool is more of like exploring what these languages can provide, or in particular Haskell can provide to this ecosystem. And in Haskell is used as the base language of the cells. Well, we have some syntax sugaring for facilitating the interaction with the ranges at the cells. But the whole spreadsheet is a Haskell program, and users interacted in what you see is what you get way. The tool is available in this GitLab. And these are the main design principles. We don't want any backwards compatibility. This is just an exploration tool. We don't want to import existing spreadsheets. We just want to explore. But keeping all of this design that is so successful with these tools, and in which you have a what you see, what you get interface, you type in the cells, you see the results. But we wanted also to provide a separate code editor to write some functions that we later are going to use in the spreadsheet. And in the cells, we will be working with basic types, but also we explore the idea of introducing some aggregate values, some complex data types, to facilitate the interaction and the computations. There is a separation between the representation, the appearance, and the internal representation, such that you can implement your own show function, or to differentiate between how do you write the data and how do you see it on the cells. And at the end, everything that you write, it's translated into a Haskell program, in which you can have all of the benefits of the languages and all of the optimizations of it. This is an example spreadsheet to have an idea about that. This just represents the grades of an student on different subjects in a computer science curricula in Technical University of Madrid. And in the first four columns, you have the year, the name of the subject, the amount of credits, the grade, and the final qualification that is derived from the previous one. We have a validator function that checks that previous values are correct. And in the last two columns, we have some calculations regarding the grades and the amount of credit, successful credits. So let's take a look at how did we write this spreadsheet with the Haskell language. In the cells, you can write any Haskell function. You can call any already defined function, for example, sum, and apply it to a range of values. Or you can start to compose with the thick width, fold, reduce, and everything else. You can reference other cells, and the notation for the ranges, which is similar to a list, then is the sugar into the corresponding range. On the external module, on the companion code editor, you can define your own data types, just as in Haskell, and use it to define functions that later you are going to evaluate in the spreadsheet. In this case, we are working with more complex types. For example, how to handle errors in the calculations of grades using the either pattern. But we can also introduce new types. Oops. Okay. New types. Because it's an already known and very used pattern to prevent errors when you are working with the same types. For example, with numbers, and you don't want to switch the order of the arguments. That's a very common error, especially if you are referencing cells, which are not specifically typed, or you cannot differentiate the name just by the reference. So new types are supported, as in Haskell. And then you can define your own aggregate data types. And in particular, we have a notation to call, for example, ranges of cells that later will be used as arguments. So as the same way that we convert ranges to lists, we can also apply them to the data constructor. There's more features, for example, as I said before, how to apply data validator, that you can define a validator that is triggered after each cell evaluation to know that everything is properly written. But there is one more important thing that we have done, and that is the treatment of blank cells, because usually they are an essential feature of spreadsheets, and we have to deal with them here. Blank cells are a fundamental feature of spreadsheets, but it is also one of the source of other errors, because at first you can perform calculations without incomplete data. You have a table with empty cells. You can reference it, apply sums. But when you have to handle more other complex cases, you need to start to detect when are you working with a blank cell, an empty cell, when it is an empty string, which is different. And also, it is not clear how systems or spreadsheet systems deal with empty cells. For basic additive usage, you can always replace it by a 0, but this does not apply to other arithmetic operations. You have the division by 0 error, or even in non-arithmetic contexts, you need to, as I said, to deal with questioning if is it a blank cell, is it empty strings, and also you can receive an empty cell as an argument, but you cannot return that in the spreadsheet. You need to convert it to an empty string. Also, different spreadsheet systems deal with empty cells differently, so you cannot port it to other programs. This is a problem with current spreadsheets. And the thing that we did was to propose a system of default values that we will apply when we reference empty cells. For a single cell reference, we can replace it by a default value. So, for example, if we call A4, we say, okay, if it is blank, replace it with a 1. But default values must not conflict, because if you understand that A4 is a number, later it cannot be a string, because then there is idea that one thing is representing multiple things at the same time. The default notation also applies for ranges or for lists. This is equivalent to define on the left. The list of A4 to F4 is default 1. It's like substituting every cell with a 1 in case of it is empty. But we can also extend it to function arguments. So when we define the function, we can say, when you are applying a plus, you sum two elements, for example, treat the default value as 0, or maybe the empty string, or a boolean. But it is also applicable for complex data types in this definition. And when we define, for example, our custom data type, you can say the grade, if it is empty, for example, it can be the absent grade. And we formalize all of these substitution and this default extension. Talking about the tool, Haskell is, well, three different things. The most important one is, well, the definition of the language is the heart of the system. It implements the default system resolution and implemented with template Haskell. Then we have the runtime, which provides all of the functionality related to the evaluation of spreadsheets. It receives the cells and the external module and implements the sugaring, all of the dependency analysis to detect cycles in the reference of cells. It's in charge of compiling and evaluating the module or the program, and also dealing with the error handling of anything wrong that can go in the execution. And finally, there is the Haskell application, which is responsible for the interactive behavior of the tool. It has a client side, which is web-based, and the server side, which is an application implemented in Elixir with Phoenix, and client and server communicate using a JSON-based protocol through WebSockets. As a quick conclusion, this tool is a proof of concept. The prototype is kind of satisfactory. We can interact with the cells, we can test all of these ideas, we can explore. It gives us a platform to test our ideas and how we can extend the spreadsheet usage with it. But there is plenty of room for improvement. For example, efficiency, it could be faster, or we can improve all of the usability things. Also, how do we deal with more staggering of the code? And for future work, we also consider the use of some more complex type system, not to be specifically tied to Haskell, but maybe implement or use dimension types, or introduce liquid types in the definition of cells or what they can hold. We also want to explore other kind of interactions that are common in spreadsheets. For example, autocompletion of code, how complex values or list of values, when evaluated, spill and produce a list of cells, and many other ways for interacting with the spreadsheet. Also, we don't want to be limited to just use this language implementation, but we also want to explore how other tools or languages, for example, Elixir or different paradigms, how to introduce constraint logic programming in the spreadsheet can help the development or the definition of them. This is something that have been done before, but we also have this interest and want to explore how this environment can be benefited for the use of modern programming languages. And I have a quick demo to see the tool, and also you can ask questions during the demo to see and explore the system. And thank you very much. So this is the tool. It looks like modern spreadsheets. You can evaluate code slowly, because one of the things, I forgot to turn up not the power server, but the performance mode. So one of the things why is it kind of slow is that for every cell update or input value that we do, we are generating a Haskell program, compile it, then run it, parse back the results and possible errors, and then we have the result. This is just the most basic implementation that we can do. But starting from that, we can start, for example, to use the REPL for interactive usage that could be faster but not different, or should not be different than compiling your program and execute it. We can reference cells, for example, itself. And if it detects an error, for example, a cell reference, we know that because of the dependency analysis. We can also reference, for example, the cell next to it. And if we do that, the error that we get is that we are referencing a black cell without a default value. So we can say, okay, we can say that the default value is a string PADL, and if it does not find the cell defined, you can reference it here. We can also have some Haskell definitions. For example, say that x is an integer, and then we have it here, the x. Please don't, okay. Oh, sorry. Well, this is great. Now it is a 3, and PADL should have been updated. It is not, probably because it broke, but I mean, this is the demo effect. But if you have any question regarding this system or want to have an idea or you want to ask anything, please feel free to ask.
We have plenty time for questions, so please.
During your demo, which one of the errors were errors that your program detected, and which one of them came from the compiler?
This compile error, the loop error, it was parsed from DHC. All of the dependencies error are done before compiling to the program. So in case that we detect, for example, a cycle, it is done before executing it. And also every time that it detects an error, the dependency analysis detects which cells are separated from proper evaluation from error evaluation, the error side, in order to keep, for example, the first value evaluated and not breaking the whole spreadsheet.
So why is B not updating?
Let me see the logs.
Okay. Would that be a type error anyway? Because you have a string default value and you have an integer in C.
So it's not returning the result. I'm not sure why. Then if you change the value of cells until they are not evaluated, they can change the.
Yeah, but is this a type error?
I don't know. It's a very interesting question. We didn't know about that. With that. But yeah, that default substitution with different types might be a source of type errors, and that's a good thing to look for.
The only thing we guarantee for default substitution is that it terminates. As there's no circularity between what you write in the right panel and what you write in the cells. So in the end, you obtain infinite time. You obtain a Haskell program, and whether it compiles or not is another question. It might be rejected by Haskell.
Yeah, I wonder why did you choose this Haskell programming language for this project? It seems to me that for spreadsheets, perhaps an eager functional language would be more appropriate. So what were the reasons behind this?
As I said, this can trace back to our final degree project, and at that time we happened to like Haskell, so we started working with it. But what we noticed that lazy evaluation might only apply or benefit here in very specific computations, is if you define infinite lists or work with infinite lists here in the spreadsheet, and probably an eager evaluation system.
Yeah, besides that, for instance, I don't know, you use Haskell template. Is that useful?
Very easy way to implement this kind of extension in the language, because
it's a very mature language, so.
Works. So D1 is not defined. Oh, and here is like a type error, parsed from the compiler. I think that by default, it is treating this value, for example, as an integer. So if I change that and reevaluate, yeah. So there is something error in the math. Yeah, the template we were experiencing also in this template Haskell or this transformation of programs. So we didn't switch to a different language when we implemented this. Although we, all of these application, if we go back to here, the application and the runtime is independent of the language definition, kind of, instead of the sugaring. And in this way, we have all of the framework to develop different implementations and use different languages to work with the spreadsheet.
Why the server is implemented in Elixir? You Concurrency for? No, it's actually because the Okay, okay.
Very well communication through channels, and well, we used to develop these kind of applications.
So I was looking at that type error you were getting on that last example there. Benefits, I think, of things like Excel is that it's very accessible for the average user to come and just bang out a spreadsheet to do some calculations for them. But I think if my mom were to come and see that type error, she'd just freeze up, and that'd be the end of it. So,
and the first thing that we took into account when we wanted to develop this spreadsheet system is that we wanted to use a more complex environment because we know how to program, and sometimes we find ourselves limited by what you can do with spreadsheet formulas and Visual Basic or Basic. So we don't want to be a tool that substitutes Excel. We just want a proof of concept that help us to find some things that we don't think about usually. So for example, we first had the implementation of the spreadsheet system, this idea that what if we evaluated Haskell code inside a cell? And later we started to think, oh, but we can have a separate module to define all of our helping functions, because usually the formulas are very complex. And later we thought, what do we do with empty cells? How do actual systems interact with it? What is the definition? What is the semantic of an empty cell, and how do you use it in the whole spreadsheet? And this is not defined. If you want to know, for example, what LibreOffice does with empty cells, you need to go to the code implementation and look for, if it is double, then do this. It is not defined anywhere. So it's a great environment to think about these kind of things and other kind of interactions. For example, working with multidimensional arrays, how do you reference and understand the enumeration of ranges? If they are, for example, sum this rectangle, how do you apply the evaluation? It's just a way of putting something in a strange place and see how it happens to be.
I have also one final question. In your formulas, you always have shown that you have given the concrete names of the cell, like D1, D2. Can you also parameterize the formula over the rows? Because sometimes you want to have a formula in one row which you want to copy it into another row, and then so you want to parameterize your formulas over the rows, also over the columns.
We don't have a proper syntax for referencing rows or columns. Mm-hmm. We can apply ranges for that. So, for example, if we sum A1 to A10, okay, we references a range without default values. To be working unless I didn't pull the latest changes. But we support a way to reference ranges. It is not, maybe if I understand it correctly, you are also talking about parameterizing functions, maybe regarding receive a list.
more cells, because sometimes in spreadsheet programs you have the possibility you copy one row into another row, and then all the cells which are updated related to the other row. And so you have more, and if you want to have this flexibility, I need some parameterization over the rows.
Rows around, because then you will need to update all of these cells. But later, all of the columns or maybe rows could be just understood as a list of cells and work with that.
Mm-hmm. Okay, so thank you very much again for the demo and the discussion. So, and now.
Okay, so
The scenic route to deforestation, and presented by Vincent Robinson with his co-author Stephen Libby from the University of Portland.
So this is a presentation. I'll be talking about this, proving the validity of this specific compiler optimization called full-dar build deforestation in the functional logic language Curry. So deforestation is a general optimization technique that's just concerned with removing intermediate data structures. So if you have something that produces a list and another function that consumes the list produced by it directly, then you didn't need to create that intermediate list at all. It's just extra work for the garbage collector to be doing. So for instance, we've got this all function here, which checks in Haskell. This all function checks if a predicate holds for every value in the list. The direct way, in my opinion, is just to map that predicate along the list to get a list of Booleans, and then AND up all those Booleans together. That creates an intermediate list. We could also write it without the intermediate list by using full-dar and just saying, okay, apply the predicate to this element in the list and AND it with all the other ones we've applied it to so far. Which I don't think is quite as clear, but it does avoid the intermediate list. So there's this nice paper called A Shortcut to Deforestation, which notes that full-dar is kind of sort of like a universal list consumer function, because it just takes every con cell in your list and replaces it with a function. So if you say full-dar plus 0, it's going to replace nil with 0 and the cons with plus. And so if you could somehow find a way to abstract away producer functions that produce a list with cons and nils, you could just replace those cons and nils with the plus and the 0 directly. And in fact, you can do this not too difficult, without much difficulty. If you define this function build g as g cons nil, g is your producer function. You're passing in cons and nil to produce a list. So if you come across something with the form full-dar k of z of build g, then we're building a list and we're consuming it immediately. We can just say gkz, pass in our cons and nil functions that we're using for full-dar. So yeah, this is called full-dar build deforestation, very creatively. So let's see this in action here. If we here our AND function is defined in terms of full-dar. If we define map using build and then this lambda function that's going to produce our list using full-dar, so expressing map in terms entirely of build and full-dar, we will end up when we expand out our definition for all, then we expand it like, and map. So this gives us something of the form fold_r, kz, build, g. So we can apply our optimization here to get g, kz. So now we can just expand out this lambda here. And voila, we got that all prime function that we defined over there. It's pretty slick. And since map is defined in terms of fold_r, if you've got like more maps and stuff, all of those are just going to collapse. And you're going to move all the intermediate lists. It's actually pretty fun to see how it works. So there's, if you just were to naively apply this optimization, you'd run into some issues. If I make our list producer function just create the list 1, 2 directly, not using the CNN that's passed into me, well, if I fold_r this, I'll get the list 1, 2, add it up, I get 3. If I play the optimization, I'm just going to ignore the plus and the 0 functions entirely and return a list. That's not even the same type, let alone the same value. So that's not good. We can actually solve this just by modifying the types. If we give build a polymorphic type, it's basically going to say, all right, my list producer function has to give me this polymorphic b. It can't give me a list. So this is forcing g to have a type a to b to b. That's our cons function, where a is any type. Might be Boolean, for instance. And our nil, which is also polymorphic. And so it has to use those to return the final constructed thing. So it cannot create the list directly. And this solves this problem. But how do we know it solves the problem for sure? Well, we can use this nice technique called free theorems. And free theorems are really cool, and I'd love to get into more detail about it for those who don't know about them, but I don't have time. But basically, what they do is you take the type of a polymorphic function, and you get a free theorem out of it. So if we take concatenation, it takes 2 lists, returns a list. The free theorem we get out of this for a function of this type is that if you concatenate 2 lists and then map a function over them, that's the same as if you were to map a function over the first list, map a function over the second list, and then concatenate them. So what we can do is we can take a free theorem on the type of our g function over here, and we'll get a free theorem out of there, and then we substitute fold_r kz as our arbitrary function. And we'll actually just end up with the fold_r build theorem. It's really nice because the proof for this is like a little over a quarter of a page. It's pretty delightful. So this is all prior work. What we want to do is we want to apply this to the functional logic language Curry. So Curry looks a lot like Haskell. If you're familiar with Haskell, then Curry won't. You could write some Curry code not without much difficulty at all. But it's a logic language. We've got non-determinism. So specifically, we've got this choice operator here, where if you say A or B, it's going to return both A and B non-deterministically. So in a slightly more complex example, if we fold_r the choice operator, we use this failed function, just returns no values, then it's just going to non-deterministically return every single value in that list. Kind of slick. We also have free variables, where we can say if we have let x be free, and then in this case, I'm just using an example of list of Booleans, then it's going to return every possible list of Booleans. So the empty list, list of true, list of false, list of true, true, so on and so forth. There's a few other nice things you can do with Curry, but these are the things that are important for us to talk about here. So you got to be very careful in Curry, because just because it looks like Haskell doesn't mean it acts like Haskell. A lot of optimizations that you can do in Haskell don't work in Curry at all. So if we here's a double function. It just adds its argument to itself. So if we double a non-deterministic choice of 0 or 1, we should get 0 or 2. Now, what if we were to inline this function? We get 0 or 1 plus 0 or 1. But suddenly, we're making the choice twice. The first time we might choose 0, and the second time we might choose 1. So now we can get 1 as an answer, which isn't good. You shouldn't be able to double an integer and then get an odd number out. So you actually have to be more careful. You have to say, let x equal 0 or 1, and then we can do our addition. this is said to be, we're sharing the value. We're sharing the non-deterministic choice and using it twice. So, how does fold-R build do it fair in Curry? Surprisingly, there's only a few instances where it just breaks down. For the first one, if we do some tricky stuff with partial application of functions. So if we have this, here's our k function we're going to pass to fold-R. It takes our first argument, then it's going to non-deterministically choose a function to return that you can apply for your second argument. So when you partially apply this function, you get non-determinism. In our g function, we exploit this by saying let c prime equals c of 2. That's going to give us one of these non-deterministic functions, plus or times, and then we're going to use it twice, c prime of n. So if we use fold-R, every time it sees a cons in the list, it's just going to take k and fully apply it. So it might give us plus, it might give us times. So we could have like 2 plus 2 times 4 will be our final expression that we evaluate. But if we apply this optimization, we can't do that. We're sharing the choice. So we might get 2 plus 4 or 2 times 4. We've lost values if we apply the optimization. OK, we can break it with partial application. We can also break it more cleverly if we fully apply a function. So here our k function, after you fully applied it, gives you either a cons b or a plus 1 cons b. In our g function, we use a recursive let binding, where we say let c prime equals c1 c prime. C prime is using its own definition. So this is going to give us an infinite list, obviously. In fold-R, this will give us like a infinite list of, you might choose the first one, or might choose the one where it adds 1, so we can get lists of alternating 1s and 2s as much as we want. So we just look at the first two values. That's what we have. If we apply the optimization, though, the non-deterministic choice we make when we say c1 c prime, we're going to use it every single time in this recursive let binding. So we're just going to lists of 1s and the list of 2s. So again, we've lost values by introducing sharing in our g function. So the question is if we can break it with partial application, we can break it with full application. Can we somehow break this with no application? No, you can't. If we just say like k is either plus or times, it's just a choice of deterministic functions, we make that choice before we even get into the g function. So everything's fine. No sharing can happen. Or specifically, sharing always happens for fold-R and g. Our last feature in Curry we need to be careful about is free variables. Can these break fold-R build? Well, if our g function is just let's make it a free variable, and let's say we're doing Booleans, so we're just going to OR them all together with true. In fold-R, we're going to build a list, any possible list of Booleans, and for each of those Boolean lists, we're going to OR them together with true. So of course, we're just going to keep getting a bunch of trues. But if we apply the optimization, we suddenly, g is creating free variable Booleans, so it gives us true and false, because that's all the possible values of Boolean. And it ignores c and n entirely, and so we've added values. But this is actually sneaky. What we're running into here is what we were running into earlier, where g was trying to create a list directly without using c and n. Free variables are kind of doing that. They're kind of creating a list without using c and n. And in fact, this won't type check according to our type for build. Because free variables in Curry, if you're using on a polymorphic type, it requires the data type class. So this type for g is too specific. Build will reject this. So you can't say build g. It won't type check. So free variables are not a problem. They're just never applicable for the optimization. So our only two issues are partial applications and full applications with recursive let bindings. So we can't prove this in Curry like we proved the other one with free theorems directly, because free theorems don't work in Curry. Not a big surprise because the other optimizations don't. But there's this paper called Parametricity and Proving Free Theorems for Functional Logic Languages, which is a mouthful, that gives us a way of doing free theorems by translating Curry into another language. So first, it has Cumin, which is basically kind of like a desugared version of curry. It removes all the nice fancy schmancy syntax sugar, just gives us the bare bones basics. It's not entirely equivalent to curry. One of the things it doesn't have is recursive let bindings. So our issue that we ran into with recursive let bindings can happen in curry, but not in cumin. So anything we prove here is not going to be fully general to curry, but it's close. Then we take cumin and we translate it using these automatic translation functions to this language we call salt, which is a deterministic language. It uses set types in the type system to work with cumin's non-determinism. So we're reifying the non-determinism in the syntax of the language to make it so that we can get free theorems to work on this. So what might be 0 choice 1 in cumin is going to be the set of 0 union the set of 1 in salt. As a slightly more complicated example, here's the type of full-dar in cumin. It's, that's the type of full-dar in Haskell as well. But when we translate it to salt, non-determinism, according to the type, we don't know about the definition, non-determinism could be happening anywhere. So we got this disgusting amount of set types here, just showing you wherever non-determinism might be happening, which is scary, but you can simplify it, because we know that full-dar is deterministic if it's passed a deterministic function to it. So you can actually apply simplifications, and it will simplify the type, and you'll finally get a nice deterministic full-dar back in salt. So we have free theorems for salt. They prove free theorems work for salt. You just got to be a little. You just have a little more to work with when you run into set types that you wouldn't have to do in a functional language. So let's see if we can prove the things that we know are true. We know that if non-determinism doesn't happen anywhere inside the k function, that full-dar build should work. So in salt, that's about equivalent to saying k is a set of deterministic functions. So our type of g, after we've simplified out all the set types, we take a deterministic function and a nil value, and then we can have some non-determinants inside g. And the proof for this is basically the same as the functional version of full-dar build. We've got to do a little more careful. We've got to be a little more careful with the set types, but it only adds like a line or two to the proof after you've built up the framework for free theorems. Now we should also be able to prove this one where if it's fully applied, you have non-determinism, because we don't have recursive let bindings. This should be true in cumin. Now G has this. G is passed a function that may be non-deterministic when fully applied. This actually makes proving things significantly harder, because in this first one, full-dar is deterministic because you're passing it your deterministic function here, in full-dar's case. But once we get here, and when we have a deterministic full-dar, we can just substitute in, like I was saying earlier, when you take the free theorem for G, you substitute full-dar kz as one of your arbitrary function thingamagummies. If you just substitute it, suddenly full-dar is now non-deterministic. So if you just try to substitute it in, you're going to end up with the set of a set of B, which isn't good, because once you've got a set type in salt, you can't really get rid of it. You can't get rid of non-determinism once you've introduced it. So what you can do, though, is you can apply the free theorem twice. You can relate the set of B to the set of B, and that's related to the set of B that you got from applying it the first time to get full-dar, what you were hoping to get was full-dar build. And basically, you can just eliminate that middle term, and you get that it's equivalent to full-dar build. You get the full-dar build theorem out of it just by applying it twice. Lastly, can we prove it for the case where we have non-determinism partial application? No, we can't, because we found a counterexample. That doesn't work, which is too bad. Sure, it would be nice to have an optimization that worked in every single case without having to check where the non-determinism is. But wait, look at this k prime function here. K prime of AB equals k of AB. Is k prime equivalent to k? Because if you're in Haskell, it sure had better be. But since I'm asking this question, the answer is probably no, as you can guess. No, it's not in curry. They are totally not the same. And you can see this easily when you look at the types in salt after you've simplified them.
The type of k in salt, well, we can have a set we could have non-determinism anywhere. But in k prime, we've fully applied k. We've pushed all the non-determinism to the end of the function. So basically, partial applications of k prime are deterministic. So if you say k prime of 1, you're going to get a deterministic function back. Only when you fully apply it do you get non-determinism. So this is useful for preventing sharing problems. Full-dar never introduces sharing, which we established before. So full-dar of kz is equivalent to full-dar k prime of z. And it's pretty easy to prove just by translating it to salt and checking to see that everything's the same. But using k prime prevents g prime from introducing sharing anywhere, because g can't do its sneaky stuff by partially applying things, because partial applications of k prime are deterministic. So if that's equivalent to that, and that's equivalent to that by the full-dar build theorem that we proved earlier, we've got a fully general full-dar build theorem just by introducing this k prime function that works in every case, including partial application, which is really neat. We've got a full full-dar build theorem. So the key takeaways, I think, from this are, first, full-dar build is mostly 95% valid in Curry. You've got to be careful about features like recursive let bindings that don't work in Cumin. But full-dar build, most of this is happening as compiler internal definitions. So as long as you're careful not to use recursive let bindings, you should be OK. But a little more than that is, as a broader takeaway from this, is like we proved a single optimization is true or correct, but there's some more. You can look a little broader than this. So Curry's problems are due to sharing. This is not news for Curry in terms of optimizations, but fully applying functions like that k prime function fixes problems with currying. A lot of the problems we ran into, a lot of the simplifications we had to make to salt code, was because non-determinism could happen anywhere in those partially applied functions, which results in a big mess. Funnily enough, currying causes most problems in Curry for us, which I think is funny. But also that free theorems are actually really powerful. What we did with applying the free theorem twice to deal with passing a non-deterministic function in is something that the original paper that found free theorems, they didn't notice you could do that. Or if they did, they didn't put it in the paper. So free theorems are actually able to deal with a really complicated problem. Full-dar build makes a nice case study of the power of these in Curry, or salt, I guess, technically. And so, yeah, I think it's pretty neat. And I'd be happy to take any of your questions.
So, and we have time for questions. So, Julio.
I think I'm mostly obliged to to make some comments or some historic comments about this. So, as you may probably know, during the story of Curry was originally deterministic language semantically, although it supported a non-deterministic execution in presence of free variables. But the explicit non-deterministic choice and the free variable construct are relatively recent. They appear around the 2000 maybe, or in the 90s, at the end of the 90s. But there was a moment where they were introduced to the language, and some people, including me, opposed to the introduction of those constructs because we were aware that so far we had a language with an equality semantics that allowed for algebraic problem transformation. And after introducing them, we were all aware that we could not do most of algebraic problem transformation and free theorems and so on. On one hand, if you have the explicit non-deterministic choice, you have more freedom to write very concise programs, a la Prolog, so to say. And on the other hand, you could simulate non-deterministic choice by using this breadcrumb transformation. So you use a deterministic program, and then you annotate the non-deterministic choices, and you have this tree that you can flatten and so on. So mostly what they call cooming and this problem transformation is something that was in the folklore of the Corey practitioners, and some people consider this was not really necessary, and it was best to keep the old-fashioned equality and problem transformation. So in some sense, when I see this work, it's like remembering an old discussion, and okay, maybe we we made the wrong move in adding this to the construct and so on. Other than that, thanks for the talk.
So, any other questions? So, Herman.
If I remember well, one of the problems of shortcut deforestation in Haskell is that it's not easy for the user to write functions in this particular form. One solution, I think, is that many of the functions in the prelude are implemented in this way, and therefore, if the user uses these functions in the prelude, then shortcut deforestation can be applied during compilation to optimize the code, etc. You think something similar can be done here, or because my impression is that it's even a little bit more difficult than in the case of Haskell to write functions in the right form.
Yeah, so to answer that question, the standard way to handle shortcut deforestation is exactly that, is to define all the standard prelude functions in terms of build and fold R. So this work is built off work I did earlier when I wrote an optimizing compiler for Curry, and that's exactly what we did, is like just all the stuff is in the standard prelude. This could also be extended with something like Stream Fusion, but we'd have to prove that correct first, and we haven't done that yet, so.
To that, something I did not mention, if we go all the way back to the type of build. If you look at the type of build, we use like this nested for all type. That's not something you can do in standard Haskell. You need to use a compiler extension to get that. The type of build just cannot be expressed in Haskell without extensions. So you can't expose this build function to the user, so they can't really write their own very easily. You'd have to introduce some special rules or use some extensions and stuff. So that's kind of one of the roadblocks for users using it.
Yeah, so what are the practical implications of this? So is this just a formalization what you have done in the RISE compiler, or would you do more work to build this in? And then the next question is, so in which cases do you really get an improvement?
So is this just a formalization of what I've done in the RISE compiler? So partially, yes. Partially, there is actually a case that I don't handle in the RISE compiler that I should probably fix. But yeah, this does formalize the stuff I did in the RISE compiler. I think kind of further practical aspects of this is Cumin and especially Salt were really good for reasoning and algebraically manipulating Curry code. And there is, I think, a real question to be asked here of, could these be intermediate languages for Curry? There are certain aspects that we need to deal with. Very notably, recursive let has to be dealt with, and we don't have a way to deal with that. But that is maybe an interesting avenue to explore with this, I think.
Aspects of this is a nice optimization. In the original paper for this in Haskell, they got like a 3-fold speed up on really heavy list programs like the n-queens problem. So it can be very, just as an optimization of itself, it's also just really nice.
So thanks again for the discussion and your presentation. So.
test, 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 test. Test. Test, 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 test. Test, 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 test. Test, test. Test, 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 test. Test, 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 test. Okay. Good.
Check, 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 check. Check, 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 check. Check, 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 check. Check, 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 check. Check, 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 check. Check, 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 test, check, test, check, 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 test, check, test.
Test, test, test. Okay, I think we're okay now.
that needs to be adjusted is this, because in this code it's a separate slider. But I think, whoa. Oh yeah, this mixer. Okay, no, it's nothing. And here somewhere it's like okay. Test. Test, 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 test. Test, 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 test. Test, 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 test. Okay. Okay, that's the best we can do.
All right, so thank you for the introduction. So I'll be presenting this topic. In a moment, I'll be showing you a demo where we made a versatile configurator using first-order logic. So this demo was built entirely using generic tools that were already present at the university. So the first is our IDP system, which is the declarative system developed at KU Leuven, and its interactive consultant, which is its default user interface. So often a lot of ad hoc scripting is still required to get to the point where we can use these tools. And our goal here is to reduce the amount of work for a user to get a working application. So if you look at our interactive consultant, we see like this is the web shop for laptops. And so there's a lot of choices a user can make. So say a user says, I want my internal memory to be maximized. So if you do that, you see that internal memory goes to 32 gigabytes. And from the original 60 laptops, from the original 60 laptops, you can see next to the product code, only 4 remain. And if we look, our system also has propagated that there will be an SSD. And if you open the drop-down menu at brand, we see that only 2 brands remain. So it will be a Dell or a Lenovo. So far, so good. And say that we further want a laptop that's as small as possible, so to be practical, to take on a plane, for instance. Then it will say that the display diagonal is 14-inch, and it will further fill out the options to give you the product that you want. So this is great. This works. But how is this powered? And if we look, it's powered by the IDP system. The IDP system is a declarative system, as I mentioned. What's unique about this system is that it clearly follows the knowledge-based paradigm, which means that there's a strict separation between the user knowledge, so our knowledge base on the one hand, which is the Sunderland F dot in, and our inference engine on the other end. So the inference engine is based on Microsoft Z3 and is able to carry out different inference tasks. But our knowledge should always be completely separated from that. So if we write our knowledge base, we don't know upfront what the laptop knowledge will be used for. Now use it to power a web shop, but it could be anything really. So FO dot, then when I talk about the IDP system, I'm talking about the full system. When I'm talking about like our knowledge base or FO dot, I'm talking about the language that's actually used to write down our knowledge. And this FO dot is just like first order logic with extensions. So the extensions are inductive definitions and types. So what does it look like? This is a simple map coloring problem. As you can see, it has 2 types, type color, type country. It has a predicate border and a function color. So then in the structure, we define these by enumeration. So you see this is a partial model of the world, so there's no definition for color. And in our theory block, we are able to add constraints such that if 2 countries are neighboring, then they have a distinct color. Finally, there's a procedure block, which is an optional block that's used to, if you want to run this directly, you can tell what inference task you're actually expecting. So here will be a model expand. And if you pass this to our inference engine, it will be able to give you a completely colored map. Or if you pass it to our interactive consultant, and you, for instance, select that Belgium should be red, then we'll immediately be able to tell you that since Belgium and the Netherlands share a border, that Netherlands cannot be red. So I've explained our interactive consultant. I've explained IDP. So we now have the working blocks from what was already there. But up until now, to get our knowledge into the system, we used ad hoc scripts. So users came to us with a bunch of knowledge. We manually created a knowledge base, and used this to work it. But when I asked my colleagues, does anything exist? Everyone had written at a certain point, had written a script to transfer tabular data to FO dots. So I thought, can't we study this from a more logical perspective? Can't we derive a logical vocabulary automatically and transform our data to this logical structure? And if we have this, can we also use this to combine data from multiple sources to get a working application? So that's exactly what I set out to do. And that's why we introduced our knowledge base API for Python, or GBAP for short. So as you can see, we have a bunch of input languages. input paradigm. Like if whatever you can create more inputs. For instance, we're also looking to translate RDF triples. Once you pass them, we go to a language agnostic logical specification, which we can then add or remove predicates functions from, or merge with different specifications. And then we can pass them to solvers for different languages. And since we were able to rely on some prior work, we even have partial ASP support for that. So I've introduced a problem. So now the remainder of this topic, for this talk, I'll basically be going over like what are the different steps to go from a table to an FO dot specification. And we start with this very simple example with students and courses, and students have a grade for a course. This very simple problem is very easy to translate. As you can see, each column represents a distinct type. And the possible values in the structure for this type are simply the set of values occurring in this column. Great, so this relies on 3 assumptions. Same identifier means same real-world object. So the programming course in row 2 and row 5 is the same programming course. And the unique name axiom, programming and maths are 2 distinct courses. And the closed world assumption, there aren't any courses that are not listed in this table. Do these assumptions always work? We figured like from numerical data that might not be the case. Because for instance, if you look at our grades, we know in Belgium, courses are graded on a scale between 0 and 20. But no one, for instance, scored a 20. So if we want to, for instance, say like a perfect student is a student who obtained a 20 for a course, we have a type mismatch. So what we decided to do for numeric types was use the built-in types. If they're all integers, we use ints. Otherwise, we use a floating point number. As you can see, that's not exactly what happened here because I do have a type grade, and it's a subtype of integer, and it is a range between 0 and 20. I was able to add this with a single line of code, but this is something that a user would have to add manually, and I'll show later how this is done. Yeah, my previous example was very simple. There was no overlapping types. But what happens the moment I add the same value occurs in multiple columns? So here we have 3 possible solutions. We just consider them as distinct types. But this will not work with our system because our system assumes that distinct types have no overlapping values. So this will give an error. On the other hand, we could consider that both these columns to be part of a single type. So both student and tutor could be seen as a person. So yeah, this option is also not ideal because now all our functions are partial functions and we lose the information that what values occurred in which column. So what we actually did was we implemented this as a super type. So as soon as 2 columns have partially overlapping values, of course, if they're fully overlapping, we can simply say they're a single type. But if they're partially overlapping, we create a super type, and each of the subtypes of a column will be, so each column will be a subtype of the super type. The great thing about this is now we can use this subtype as for our default functions. So we keep the benefit of having total functions, which makes dealing with which makes writing specifications like theory constraints for this a lot easier. All right. So we also considered the alternative of using namespaces, but when you're dealing with a single table, you often don't want to create separate namespaces for information coming from the same table. That didn't seem to make sense to us. All right, so now I've talked about the types, so the columns, but of course we need to be able to talk about the rows of a table as well. This we can simply do by introducing functions. A function will take a key, and all columns that are not key columns will have a function that will map these key columns to the type of the non-key columns. So for instance, we have our grade here. So we have our grade uppercase, which is type, and there's a grade lowercase. So every student and course combination should be unique. If there's a single column as a key column, of course, that's not an issue. There's no requirement that they should be complete, it's just like they have to be unique because, well, otherwise we can't distinguish between different rows. So I think that's obvious. Our tutor example, which I showed earlier, like a complete function, and our earlier example is also an example of this. So where do we get, then the only question is, where do we get these primary keys from? So now since student and course are the first two rows that combined are unique. But the easiest is just ask the user. Makes sense. But we also wanted an automatic way to do this. And there are three options to do this automatically. First, you just take the first X columns until you get unique keys. But this is a bit of a gamble. Like in our perfectly curated example, it works out. But what if I had set the tutors as a second column instead of course? Now we have these very weird combinations, and it just doesn't make sense declaratively. We could use a single predicate, but as soon as our tables grow larger, like our laptop example has over 50 columns, just gets unwieldy. So default, we just use an index. We introduce an index, nothing to clear about that. So with this information, we have enough to actually see how this very simple demo, because I mentioned like we're trying to get this to work in Python, how we can use our GitHub tool to actually go from our table to FO.specification. And the other thing that's really, so the first thing I have to mention is we have this configuration where I set that grades as a type grades and not the default integer. So here I overwrite the default. Here this is actually what I'm doing. I'm saying like, I have a file, which is my my CSV, my grade CSV. This is the language, the origin is a CSV. We have this configuration file. This configuration, which is a nested dictionary in Python, but could also have been a JSON file. And we have our keys. And that's enough to get this very simple demo to work. And then the final row is just like, I want to print it out, translate it to IDP33 and print it. Of course, I showed you this laptop demo at the start, and now I'm talking about this very simple example. So there's probably two issues that people are still worrying about. Like I mentioned that we can combine different specifications. So how do you do that? And the second part is, of course, real-world data has missing values. How can we deal with that? So I'll deal with each of these in turn before I end the talk. OK, so the first, merging specifications. So we have, actually, our laptop demo had two files. So there's laptop data and there's the CPU data. So if we want to merge these, again, we have an issue of partially overlapping types, possibly. Like there could be CPUs in the one file that are not in the other. Actually, we can use the same solution for that if the same type had occurred in multiple columns. So we can just create a super type. This is the default way of dealing with that. And then there's a possibility of name clashes, like for instance, if a function, if identical functions exist in two files, but the risk of that is rather small because the laptop data will have a laptop key column and the CPU data has a CPU. So they have different keys, so the chances of them actually having functions that deal with the same problem are rather small. So if this does occur, this is something that the user will have to deal with. It will just throw an error. OK, so our laptop demo, how is it construed? So we have our CSVs with laptop data. We have CSVs with processor data. We pass these. We get two specifications. We can simply merge these together into a larger specification. So there's also alternatives of leaving them separate and having them actually to have your data decentralized and having your data interact with each other. But this is future work. So this is something that would actually be interesting to look into, but we haven't done yet. Then we can add our standard configuration and constraints. So what's going on here? If I were to pass this specification to our interactive consultant, we just give you a blank screen. Why? We have a complete specification. There's nothing to be decided. So yeah, everything is known, perfect world, no issues. But of course, we need to represent user choices. And for this, so I already introduced the type brand with a capital B and a function brand to represent a row. And now I'm also introducing a constant brand with an underscore, with trailing underscore, to represent the user choices. This underscore very conveniently gets automatically deleted by the interactive consultant, so it's not an issue. And now we can simply say that my brand type must be equal. So my brand constant must be equal to the brand of the chosen laptop. And this is enough for our system to be able to handle user choice. Now, of course, why am I doing all this? So I now created this laptop demo. Now the interesting part, so now we can add custom constraints. These custom constraints, for instance, like now we have this very flexible web shop, and if I were to say, I want a user to be able to select if he's looking for instance, for a gaming laptop, then I can simply write a constraint that says a gaming laptop is a laptop that meets these specifications. I don't need to I don't need to add the column to my CSV and manually check these. Our system will handle this. And if at a later point in time, the definition of a gaming laptop changes, we can simply update this one line of logic, like this one constraint, and the system will still work as intended. So after we add that, we can pass it to the interactive consultant. We can create our custom user interface, which you probably most likely do. Or we can just pass it back to the system for further manipulations. So the sky's the limit. And so this is the entire code. Well, it's slightly abbreviated. I abbreviated configuration, which I put in a JSON, actually, in the real application, to create our laptop demo. So this is just like, this is just variables that tell me which files exist, and there's a configuration. This you have actually already seen, but with a simple example, but here I do it twice, just once for both files. Then there's a merge function. I add my default constants, and I translate it, but here I don't print it, but I save it to a file. And that's all that's going on. So in these few lines of code, I'm able to transfer my tables into a fully functioning application. But of course, there's the one thing I still have to mention, missing values. So here in this example, there's only a tutor for the programming course. Again, there are three options. But here we just introduce a partial function. So my tutor function here has a domain tutor definition, and this tutor definition is a predicate that just tells me where tutor is defined. We considered alternatives, so requiring a default value, and this is actually what I do in the laptop demo. I provide defaults. But defaults are not always useful. Or we could use the superset symbol, like for our enumerations. We also allow to use a superset instead of a definitional equality to say that we only give a partial enumeration. But there's an implicit assumption here that missing values do exist. For instance, for the weight of the laptop, this makes sense. Every laptop has a weight, whether it's known or not. But there are consequences for propagation. Like, for instance, our interactive consultant will never be able to delete these laptops. So if you say the weight of a laptop has to be as low as possible, all laptops that don't have a weight will still be in there because it will just say, like, I don't know, I have to delete them or not. And if you have a model expand, it will add a value, a possible weight for a laptop. And this weight might or might not be correct. So in the one case, I say, like, for instance, my laptop has to be lighter than 2 kilos. In one case, if I do a model expand, in some models, it will be. In other models, it won't be. This is not actually what we want. And with our partial functions, even if we do consider that all laptops do have a weight, so partial function is actually not entirely appropriate, the predicates, the automatically added predicate that says where it is defined is actually still useful because that predicate can be used to, let's say, like, I want to be sure that my laptop is lighter than 2 kilos. It's a hard constraint. I can actually just say, like, and I only want to take into account these laptops where weight is defined, and it will just remove the other ones. And thanks to our automatic default, our choice constant creator, these choice constants will also automatically be created. So in conclusion, I've introduced GitHub, which aims to reduce the amount of preparatory work required by users to enter data into our system. It's a flexible framework that also allows for many future extensions. Allows to introduce, as I mentioned already, we can introduce additional input paradigms, or we can create further functionalities such as allowing decentralized data instead of the monolithic data which we use now. So that was my talk. Thank you very much for listening.
Questions? Yes.
So part of your work reminded me to something called bidirectional transformations. I don't know if you're aware of that. In these bidirectional transformations, you typically consider two representations of the same data, as perhaps you do, like a logical representation and a database representation. And then you have a couple of functions, get and put, to go from one direction to the other. And these functions must, there are a number of laws that must hold, the get put, put get, and so on. There is a number of laws to ensure that everything goes fine. And the nice thing of this framework is that allows you to keep both representations synchronized, which I don't know is something you are interested. So that if you change something in the database, you can automatically propagate this change and vice versa. Directly applicable, but perhaps you can find some useful ideas in these bidirectional transformations.
Because I forgot to mention it, but as you can see, like after we propagate our data, like after we do a model expand, for instance, we of course also want to reintroduce these this output into our system, so get it back to the language independence representation. So thank you for that information, for the hint.
I'm not sure if I understood correctly. You said that your type names correspond to the headers in your CSV files, and you're making the assumption that the same header doesn't appear in two different files? Did I understand? Is that only because you're using a very small number of files? It seems like you're very likely to have name in 1,000 different files as a header, even if it's not the name of a person, name of a vendor, or name of a city, or whatever.
We make the assumption that the same header does not occur multiple times in the same file. It only becomes a problem if it occurs in multiple files, if you actually want to physically merge these files, which sometimes you might want to do. Like for instance, in our processor example, the one was called product code, the other was called processor. So it didn't make a difference, but both of them could have been called name. So that could have been an issue, and then you have to actually manually, at the moment, you actually have to manually rename one. But as soon as we're going to, like in the next step, I really want to look into this decentralized data, and then that will no longer be an issue, I think. Might still. At the moment, I only support tables. Yeah, so no nested tables.
Another question is, so
But no, the order of the rows doesn't really matter for the system. So just like it just extracts them like. Yeah, so for instance, so here just like, if for instance, all the programming scores were first introduced and ending, so it just translates to this, so it doesn't really matter.
of course,
Sorry?
You want to like count to 5?
Oh yeah. 1, 2, 3, 4, 5. Thank you very much. So this talk responds to work done by me and Miguel Areias, and it's a work that's been going on for a very long time. It's not as ambitious as it looks like from the first slide. So we're not actually going to rule the world, but we're trying to build a bridge to connect to different things, which is what the ring was supposed to do. So interfacing different languages is something that has been done for a very long time, since almost the beginning of having two different languages. Essentially, it's the ability to use two languages as if they are one. And it's very important in practice. It's important for Prolog, but this has also been the source of the success for Python in many ways. So do it naturally would be really great. And in this case, the goals that we have in our interface, which are the same as everyone else's, are we'd like it to be transparent, meaning that you should be able to just use the system with the interface as it wasn't there. It should be efficient. It should slow down your system considerably. It should be generic, since it should work for any kind of program. And it should be elegant, because elegance is nice. So let's go to each point in time. So people have been doing this kind of interface in logic programming for a very long time, not as long as it seems from the slide, but for a long time indeed. So from almost the beginning of the area. Quintus Prolog has the first really licensed interface that was developed for Prolog. It was also kind of similar to the Success Prolog one. And SWI has a lot of work on this area too, because SWI has been used by different communities, like the first interface, the GPL, which did the Java binding to Prolog, and Real, which we also collaborated in connecting Prolog to R, and then nowadays Janus for Python. So all these interests have been developed, and they do the same problem as what we are doing here. I wanted to talk about the differences in our interface though. So this is our beautiful design. And the main thing that we did, which is kind of interesting, is that instead of connecting directly Prolog to Python, we used C++ as a middle step. So the reason why we did that is because Python, now this is much more of an object-oriented language. And also because it makes the interface kind of neater and cooler, simpler to understand. We use a system called Swig for glue that doesn't have anything to do with SWI Prolog. It's an interface generator. It's I can say weapon with two. Well, it can be helpful and it can be dangerous. And we do the translation from our native C code to C code. Finally, we also added some libraries for language-specific functionality for Python stuff. I'll explain that later. So the foundations in the app are the C interfaces, or that were originally. The app underscore are the internal available functions. We call it app underscore because I'll call it app underscore. They're shared globally within the app, but they're not supposed to be exported. And they follow this methodology, which is essentially each data structure as a representation, an abstraction, a function to be constructed, they say, and an identifier. Okay? So we export that in a more kind of organized way, as in the C interface, the external C interface called EAP, with all the capital letters. It essentially was designed just to isolate from the engine. It tries to export engine, fix some problems that have appeared in the work. And the app also supports this PL interface, which is actually the native 6 SWI interface. And it's a totally different perspective. Whereas you build terms and access terms, SWI is more about unifying terms, getting terms, and putting terms. So it's more like actually Prolog implementation in a sense. So all these things exist within the app. And the way we did the system is something like this. We start from we had these 3 interfaces built, C, C++, and SWI. We connect C++ to Swig. We connect SWI to a specialized term constructor that does the conversion from term Prolog to Python. And then that's it. So there's lots of interfaces going on here, which makes the system a little bit slower. But they're doing different things. C++ is constructing the objects. C++ and Swig are talking about objects and how you can connect to them. SWI and the app, the lower interfaces are talking about how we can move from Python to Prolog and back. I'll try to explain that later. So the object-oriented interface, the one I should explain better here, is essentially has 4 classes, 4 types of classes. The first one is called the app term, which is, guess what, manages terms. And the second one is called app engine, which manages the engine, the Prolog engine. The app A manages the atom table, which are the long-lived objects in Prolog. And finally, the app error, which takes care of errors. So the structure is like this. You have the C++ interface. You have these 3 types of classes. And for example, terms have several classes for every possible type of term. Applications, which are compound terms, pairs, integers, lists. You can construct lists, etc. So all these things will become available directly from Prolog to Python through the C++ interface. So each one of these objects will become a Python class. The same to the database. An atom will become Python property, will become Python class, functors, etc. So all these things will become what you are going to use from Python. And if you just use it in the C++ interface, you can also do that. Actually, something of a little bit surprising for me was that I did the C++ stuff hoping it makes it easier to convert to Python, but actually it's of interest on itself. For example, this is a small program that's part of an XML reader. So the idea is that you just grab an XML package reader, which are plenty of them. Most of them are written in C++ or C. And then you just go to the C++ and adapt it to the interface to construct a term, a Prolog term. So that made it possible to construct a XML interface to Prolog in 1 week or so. So the key here is whenever you get a new attribute, you construct an application term, a compound term, and then there is some kind of bureaucracy going on, which I will not mention here because it's going to slow down things. So that's the basic idea for C++ interface. Error handling, you do it through this error objects that I mentioned. So an app error is shown down below, shown up here. So if the stack is not enough, you construct an app error object, assign it this type, and send it away. The idea is that the system actually manages to fill up the error object, and then the error object itself is neutral, language neutral, meaning that whenever it sends an error, it can be interpreted in Prolog, in C, in Python, whatever. So this is a nice thing about the interface, that you can just do the error whenever you prefer. So the way you do it is essentially by just having a simple dictionary where the keys are strings, always, and values are strings and numbers. We can have temporary values like terms, but they're not allowed between the languages. Value, you can also copy a term, but you have to convert it into a string first. That's a simple idea. So now we get to the term, to the object transformation. So Swig is the system that we use, is essentially capable of translating C++ calls or C to Python. Not everything in C++, which is almost impossible. C++ is a really complicated language, but quite a bit. It's a very ambitious goal, and what happens is that if you try to do whatever they allow you to do, You're going to spend all the rest of your life programming Swig. And I think that was a big problem with previous users of Swig in this kind of project for logic programming, because they try to use it a lot. What we try to do is to just use it for one simple task, which is to convert objects from one side to the other, and all the rest is done by the lower level. So in this case, the way we do it is essentially by using these type maps. A type map says that given a certain object of a certain type, you're going to convert it into another object of a certain type by calling something. And that is, in our case, is always a library, bottom library built in, which is doing most of the work. So this essentially our Swig file is just a set of declarations how the objects connect to each other. That's it. This is annoying, by the way. I don't know how to get rid of it. So, oops. Okay. It's based on a previous work with R. Essentially, tree walker. From Python to Prolog, just basically construct. There's nothing much to do. There's one problem with variable liveness. You have to be careful about not keeping around variables when they're left out from the stack. But that's not the problem with the construction of itself. Prolog to Python is a bit more complicated, not in terms of constructing the terms themselves, but in terms of what to do when we evaluate. Are you going to evaluate at the end or at the beginning? So Janus has the same problem. What we do is, we have a draw option. We can either decide to do evaluation or immediately, or you can delay and construct a term for reflection. So by default in Python, we evaluate, because it's a language which evaluates. Left-hand sides in Python are kind of interesting, because the left-hand side will be the Prolog. And it can be a variable, so just set it and unify. It can be an atom, and in this case in the app, you set it as a variable. Or it can be a compound term, and in this case, the app tries to actually fill in the slots that are in some compound term with the Python subterms, which can be interesting. So these are the type maps that we use for doing the conversion between Prolog and Python. So integers get to be integers, and they go sent back to integers. So Prolog to Python, and then Python to Prolog. Floats are floats, so they are floats again. So this is so far so good. True is true, which is true. False is false, which is false. None is none, which is none. So none doesn't have a special meaning in Prolog, but we adapted one. Now, atoms, we have two types of atoms. The ones which belong to regular names, which are accepted by Python. And these are converted from Python to a Python symbol, and then back to a Python atom. Atoms which are, in Prolog atoms which are not understandable as a Python symbol, are converted to strings in Python, but not back. It doesn't make sense. Strings are converted into strings which are converted into strings. Lists are converted into lists, which are, although they are totally different structures. A Prolog list is a recursive data structure. Python list is essentially an array. Tuples are converted into something called T. Dictionaries are converted into a set of items. Again, STY, for example, has a real native support for dictionaries. We don't. The app doesn't support dictionaries. It's a special term. It's just another term. But it kind of works. Finally, compound terms are converted either as a function or as a Python named tuple. Named tuples are kind of something similar to terms, so we use it very... Sorry. I was speaking too loud, maybe. And then that's it. That's the basic idea. Let's go. One kind of interesting question that we faced, and I think Jason, the same happened to the SWI and XSP community, was what we should do to translate atoms and strings. In Prolog, an atom is a symbol. And everything is a symbol. So originally, in terms of logic, atoms were everything. There was no strings in Prolog originally. But in terms of a programming language, then you have a different problem, because in a programming language, there are strings, which are different from symbols. So if you think of Prolog as a logical language, it doesn't make sense to have strings. If you think of Prolog as a language, it makes sense to have strings. ultimately, I think that Prolog is a programming language, like it or not. So we have it as strings. And when I started to make that decision, it was a very painful one for me, because I like atoms. But in the end, as the progress goes on, I've come to rely more and more on strings. They're kind of useful, really, although they're difficult to implement. So that's the decision we've taken, which is different from Janus. Janus also had to make this a similar kind of choice, and they decided to keep atoms as strings, which I don't really agree in the end. Notation. So in Prolog, a call to Python is something like this: a.b. A is the module, b is the function. So it's exactly what you have in Python, except that Prolog interprets it as a list. But you don't really have to know that, hopefully. In Python, we use name structures. Like, for example, you can construct a term by using a as a variable, which is constructor, b as a variable, which is a big constructor, and then let's do a term called current predicate, which has a and v. So you can construct, using these named tuples, you can construct any Prolog term. Now this is an example. It looks a little bit complicated, but it's not as much as it seems. So this is a user interface usage. In this case, the idea is to actually exploit, to understand ILP, inductive logic programming, that our colleague was spoken before. So the idea is that in ILP, a lot of the work relies on having what people call a saturated clause or bottom clause. The bottom clause, the example that you want to prove, is usually in the middle. And what the bottom clause gives you is the relationships that it has in the database. So you can see each node in this graph as a path, as a node that is connected somehow to the predicate that you want to learn. In this case, you wanted to learn if this drug is active, atom is active, sorry. And to do that, you have these connections. But what the bottom clause usually tells you is very hard to understand, because it's about, say, 800 literals followed one by the other. So the goal here, what I did in this example, is to transform the bottom plot into a graph, which is easy to do. And then essentially just paint the graph according to the names of the predicates that are being used. So you can see that, for example, these red ones are atoms. These are comparisons, and these are bonds. So this is a chemical example. So the atom is a drug. The compound is a drug. The atom is a part of the compound, and the bonds connect the atoms. And you can see that actually the way the structure is connected, created by the red saturated clause, is as a kind of a circle, which sort of come out from this active example. So basically there are the atoms which are close to the example, and as you go further away, you get to the bonds, etc. And that means in practice that when you exploit ILP, when you generate clauses, you're going to generate lots of clauses with atoms because they're closer. And then you're going to generate eventually atoms with examples. And then this kind of complicated stuff that we put connected extra predicates that we generated are going to be hardly used because they're not going to be enough time. So this was the first step of this revision project that I did. Continue doing that by actually trying to quantify this. See which nodes there are more or less easy to use. So the actual code that does this thingy is this. This is a Prolog program, which is actually more like a Python program than a Python program. It generates the graph. It has the edges and the nodes. So it first defines two lists for the edges, sources and targets, computes the edge weights, and then it activates this blocks, D3 blocks module from Python, which does the real work. Actually, the real work is done by the D3, which is a JavaScript toolkit. So now what it does is, to call D3, it needs to create a data frame, which is pandas. This is Prolog code, by the way, from the dictionary, which is created by us using this notation that I mentioned about: sources, targets, and weights. Then it calls the elastic graph algorithm on this data frame using this file path, which is where the answer was stored, and the fixed size, because it's going to be pretty large. And then at the end, it sets information about the 3 nodes and calls the algorithm the elastic graph to show the result. So that's actually just the code that we used. It's basically the Python code plus the Prolog code to construct things. It's actually too much similar to Python sometimes, I think. Because if you forget, for example, in Prolog, you cannot have atoms or constants with low uppercases. So I always get these extra variables in the middle. Because it's also actually something that you cannot do in Python that you can do in the interface, which is actually you can use these digit blocks. It could be a variable, and I could actually bind it dynamically at runtime. So I could construct these objects as I go along. This is an example of a Prolog interpreter. It was written in Python. So the core of the interpreter is just this simple algorithm. You have an engine, which has the query. It seeks to extract the query from the engine. For every element in the query, if it has bindings, add it to the engine bindings, the bindings list, print the bindings, if then go on. So basically, it's like in Genus as well, you just have to do a loop to get all the solutions for the query. Just this for I and Q. And that's about it. So I I've been using this for a while. I used it for a big application in mining, actually health data. And then this ILP has been used mostly for visualization, which is something that you can do with Python much better than Prolog, I can tell you. And also to interface Prolog to machine learning toolkits, like, for example, all things from neural networks to classical learners. So all these things work pretty well. The trick, though, is that you don't want to use interface very often. You want to have it around, but you want to do a few operations which move a lot of data in a single go. If you put a lot of fragmentation, then your system will become unstable and slow. Okay, thank you very much for listening so far.
Can you say a little bit about, I don't know hardly nothing about Prolog. How does it handle numbers? And are they compatible with Python's numbers, big ints, rationals, floats, IEEE, et cetera, et cetera?
Prolog systems, most Prolog systems like YAP and SWI, do handle big numbers and rational numbers. I think SWI also handles big floats, and I don't. YAP doesn't. The interface right now, I don't think it's supporting big numbers, but not so much because of Prolog's fault. But when we did the interface first, Python didn't have this supported standard. Now that it is kind of standard in the language, I think, then it probably is quite easy to include it. So essentially, what we want to do is to convert numbers from one side to the other. We have a minimal representation, like, for example, if you have an array, you convert it to a list. But we avoid doing that until the very end, because we might lose information. If you have a NumPy array, it has more information than what is suggested in the numbers there. We always be careful of not having conversions between types, in the sense that if you have a float, you should keep on having a float. If you have an integer, you should have an integer. Never to do something like convert to text. We tried doing that in R, the R real interface. It's a big mistake. Anything that is a float, if you change it, print it out, and read it back, it will be different. And it will create all kinds of bugs for your users. So we don't ever convert in the numbers between the two systems. It just transported from one side to the other. Does that answer your question?
Cost, but you don't convert it? Isn't that a contradiction?
I just stripped the tag, convert it into the format. I have an integer. I have an integer of equivalent size in both systems.
So you send it over to Python. Python sends the same number back.
This is based on libraries, so there is no piping or something like that. It's just memory, shared memory.
Other questions?
So Aniliu didn't mention this morning, but she recently presented an approach the last ICLP, I think, an implementation that combines Prolog and Python to have an interface with an LLM. So perhaps the interface that you have developed could also be useful in this for this kind of applications, because this is quite popular now. You can use Prolog for reasoning and an LLM as an interface, as a human interface for natural language. So perhaps this is another area where your interface could be useful.
There's stuff already, so it's not the interface usually is not that difficult. You have to support. They have an interface to. It's called to Torch, PyTorch, which is a library where most LLMs are based upon. So, for me, from that point of view, an LLM is just another PyTorch object. So it's easy for me to construct an interface to that. Now, whether I want to do it or not, there are other interesting things that you can do besides LLMs. Even in machine learning, they have a nice work, which is also quite challenging for logic programmers on the graph networks. And also various which are being open now in terms of machine learning. These LLMs work, but also graph neural networks, causality, that was mentioned before. And I think that having a way of communicating quickly with this community is very helpful for Prolog, both for YAP and XSB and SWI. And other Prologs, of course. So I think it's really important. That's why you should listen to my talk. Well, I have to listen.
Other questions? So in the title you mentioned the inductive logic programming. So is anything very special in interpreting ILP and Python as compared to the Prolog to Python?
I think it's more like you have to be. So examples and most of the LP data is stored as either facts or lists usually, either dynamical lists or statically as facts. In Python, you usually use NumPy arrays or nowadays they call people tensors, which sometimes are built on top of the NumPy object. So it's nice to have an interface that can quickly copy arrays from one side to the other. And that's something that actually I have supported from the beginning. But it's not even necessary. But if you do it, for example, if you copy once time, then you can run the algorithm. It will probably take more time than the copy, much more time. Usually the more data you have, as I said before, the slower the algorithm will be. And so the less the data will actually care.
Okay, so thanks.
who's going to talk about Mola.
For the introduction. So I'm Felipe Gorostiaga, and today I will tell you about this runtime verification engine factory that we have called Mola. One goal of our group in a few years ago was to implement a language for runtime verification that would be easy to extend for new application domains. So after some work and due to some reasons that I will tell you in a minute, we came up with this, which is an implementation done as an EDSL in Haskell. And it was pretty good. I mean, it is easily extensible, obviously, but it also has a few drawbacks that you can probably already see. So in this work, we wanted to tackle that, and to do it, we introduced a figure of, we unfolded the work in two. So on one hand, a theory engineer would write the data type for the application domain in Haskell that would get compiled, and then a specification engineer will write the specification as it was intended in the first place. So in this talk, I will tell you how and why we did that. So a little bit of background first. In runtime verification, we take a specification, and in static time, we derive a monitor from it that we then run alongside the program that we are evaluating. And the monitor will receive observations regarding the program, and it will produce results. And if you do all of this, if you define your specification in terms of streams, what we are doing is stream runtime verification, which is what we are working on. Lola is a language for doing runtime verification based on streams, in which the system data is captured on input streams and output streams are defined over other streams data. And the main aspect of Lola, the main characteristic, is that it poses a clear separation of the temporal and the data aspects of the language. So the defining expression of an output stream in Lola is either the application of a function to other expressions, or a ground value, or the value of a stream at the current time, or the value of a stream with shifted by an offset. And if you do that, you have to specify default value to use when the offset falls off the trace. So even though Lola separates the temporal and the data aspects of a language, when we went to implement it, we realized that we were investing a lot of effort on parsing constants, variables, functions, doing type checking and stuff, and not so much on the temporal part of the language, which is that we were interested on. So it ended up looking something like this. And to overcome this, that's the reason why we decided to do it as an EDSL in Haskell. An embedded DSL is essentially a library in the host language. And since Lola is an incomplete language because it doesn't impose an application domain, what we have done is using the types and functions from Haskell to complete the language. And once we have done that, we deep embedded the resulting complete language back into Haskell. And this implementation, we have called it HLola. And it benefits from the type checker, the parser, the ecosystem of Haskell together. But of course, it came with some drawbacks too, right? As I showed you before, this is an HLola specification, which obviously doesn't look like a specification, right? And it has many drawbacks. For example, to begin with, we have duplicated values because we had to treat them both at the language level and as symbols. We also have a preamble for every specification that was always there, and we couldn't get rid of it. Obviously, as I said, this is a Haskell program, and the syntax of the part of the specification diverted completely from the original language. For every minor change in the specification, we had to recompile the whole stuff. And also, finally, and maybe most important, is that the errors were very cryptic. I mean, the errors were in the realm of Haskell and not in the realm of Lola, which is what we expected. So we wanted to get rid of these drawbacks, but we also wanted to maintain the extensibility of the EDSL. So we came with this with this intermediate solution that which is this meta interpreter or the engine factory that we have called Mola. Mola is built obviously on top of HLOLA, and in HLOLA we have defined a data type for the Lola expressions, which is pretty simple. An expression can be either an element of the theory or the application of an expression to another expression or a stream access. And we can think of a Lola expression as a tree in that data type. So the first thing we did was get rid of the Haskell values and define a stringly typed expressions in which anything can be applied to anything, and the parsed tree only has symbols as the leaves. But now we have to come up with a way to give meaning to these symbols, and that's when the theory engineer steps in. And the job of the theory engineer is to define a table binding every symbol of the theory to a Haskell value. And for example, given this theory of Booleans, we can already define and make sense out of a Lola specification like this one. But then we realized that we can also use the HLOLA constructors as part of the theory itself. So we have bound these constructors of the Lola language to symbols, and that let us get rid of Lola specific operators, and the stringly typed tree that we parsed now is agnostic of HLOLA. And the only difference is that now an HLOLA expression doesn't have a corresponding tree with the same shape, but instead, in this case, the HLOLA expression leaf 5 is the application of the symbol leaf to the symbol 5. In Lola, it is useful to have integers, and in fact, they are necessary because you have to use them for the offset expressions. So you need integers, and so we had to come up with a way to deal with them. And one thing we couldn't do was to add every symbol to the theory and bind them to the integer. So what we did was obviously writing a return function that would take a symbol. It will look it in the table of the theory, and it is found, then it returns that value. Otherwise, it tries to use the Haskell's read data class to get a value of the corresponding type, and if it succeeds, then well, that's the expected value. And doing this, we could also get rid of the Boolean ground values because they implement the read data class. So our Boolean theory now it's even more minimal than before. And now with the theory and the stringly typed parsed data type, all we have to do is replace the leaves in the expression, and we get a similar expression with the same shape, but where the leaves are already Haskell values. So from this, given a theory table, we were able to decode the expression with the leaves with Haskell values. And now that we have this, which is a tree of applications, all we have to do is evaluate it. It will return a Haskell value, which upon inspection, we will see that it is an HLOLA expression. If it is not, then there was a type error of some kind somewhere, and it will show up. So now we can go line by line on this example specification and see what our tool would do at every line. So for the first line, this is just a definition of an input stream with a name and a type, and that is what we do, which we just create an HLOLA stream. The same goes for the second line. And when we come to the third line, we see that it has a defining expression, which we easily parse to this stringly typed expression. We use the theory table to convert it to a similar tree with real Haskell values. We evaluate it, and we bind the result to the name of the stream. And that's it. That's essentially how it works. But in the definition of x implies y, we can see that the symbols for x and y appear. So when we are translating these, we want these two to resolve to the recently defined streams. So at this point, these streams have to be part of the theory, right? But since a stream can refer to itself, we have to do that as we are processing the specification. But we can do it recursively and everything works. So as we are processing the specification, we add every symbol of the defined streams to the theory themselves. And when we wanted to include the HLOLA constructors as part of the theory, we found out that we had to implement polymorphism and type inference. So now our theory tables not only have ground values, but they also have an annotated type, which can have type variables. And we had to implement type inference and unification to make sure that everything was well typed. So given a stringly typed expression, the first thing we do is use the information of the types in the theory to infer the types of every leaf. And once everything is well typed, and we have checked that, and everything could unify, and there were no problems, now we're ready to decode the tree and evaluate it and bind it to the output stream. And that's essentially how it works. So in summary, what we did in this job is introducing this middle player, which is the theory engineer that will write all the Haskell code with the data type for the application domain. And we have separated that role from the specification engineer who is in charge of writing the specifications. So, in conclusion, we have seen that, in our work, we saw that empirically that an EDSL is a fast implementation of a prototype language. It lets you play with the constructors and polish it, extend it, and very easily. And it's useful when the developer of the EDSL is also the one who uses it, because they are proficient probably in the language itself. But an end user will usually expect an interpreting implementation. So the error messages have to be in the realm of the tool itself and not the underlying language. And usually losing the whole power of the underlying language is acceptable. So with Lola, we found a way to move from an EDSL to a finally interpreted language, maintaining extensibility with symbol tables and with polymorphism and type inference. And we were able to do all of this without losing type safety. And if you want to play with the tool, it has a dedicated branch on the mother repository of HLOLA. And yeah, you can go there and play with it. And yeah, and that's it. Thank you.
Thank you very much. So, any questions?
Thanks for the talk. And well, if I understood it well, I think that you specialize the meta interpreter for a given data theory in order to get something which is, I guess, more efficient and faster and so on. So how do you do that? I mean, are you using a particular partial evaluation or a specialization technique? Are you using any tool for that? Or are you doing that by hand? How do you do this specialization?
Hi, can you hear me now? Yes, there's two steps, right? You have to define the theory by hand in Haskell. And once that is done, what you get, you compile it with GHC. And what you get is an interpreter for a given application domain. I mean, we have done heavy use of the reflection package of Haskell to make sure everything is well typed and there's no ugly runtime errors. But that's how it works. I mean, given the application domain, the specification engineer can use those types and functions in their specification. I mean, Mola is in that sense meta because it doesn't come with, I mean, it does come with a few application domains, obviously, but you can, a Haskell programmer can easily extend the application domains. That's what we are selling. I mean, it's not fixed and it's very easy to add new theories. So it comes with booleans, integers, doubles, and I mean, if you go to the repository, you will find example theories for handle UAV flying monitors and applications to the blockchain. So but those are examples, and then if you have a new application domain, you should, if you are a Haskell programmer, you should easily add your new data types and functions for them to be used in the specification by a non-Haskell expert.
Okay, if I understand what you say is that it's actually not a partial evaluation or a specialization. You just add more information, this data theory. So anyway, I think that perhaps partial evaluation or specialization could be useful to get something more efficient. It's been used for domain-specific languages in the literature precisely for that. So you write an interpreter, and if you want to get something, a more efficient interpreter, you can specialize it for a particular strategy, for a particular theory, for a particular program, for a particular anything. It's a way
into optimization.
Something which is faster, which runs faster without any special effort.
I see. What you are proposing is if you are using only integers or only bitmaps, then you can make it more efficient if you are aware that those are your application domains, right? Yeah, sure. I mean, we should definitely take a look into that, yeah.
Just maybe not a question, but just following up. I think so. In monitoring applications, if I'm not mistaken, if I remember properly, even the non-super efficient implementations would process like thousands, even tens of thousands, hundreds of thousands of events per second. So the difficulty that I think was accomplished with this work is to refactor a tool that is built for, say, for example, UAVs into a network processing monitoring tool. And with tools like this, you can do that in like 2 days, for example. And then your users will be, for example, network processing or say denial of service attacks software developers or engineers. And 2 days before, the tool was specialized for UAV flying. So it was on board of actual UAVs. So it's not so much about speeding up the tool, which could be great, but this is not the purpose. Is how do you transform a tool that was conceived for embedded systems into network processing, for example, or blockchain analysis. And with this, it can be done in like, 200 lines and maybe 2 days without having to go through a complete refactoring of the whole software. So I think it's about flexibility, not so much efficiency, right?
More questions? Can I ask you a small question? So, Haskell to generate the code. Then you're also going to have to do the Haskell libraries as well, right? At the end of the day. Imagine if you wanted to plug this in UAV. Would that be too much in terms of space?
But I mean, you're worried because of the fact that we are using Haskell, right? As they are. Yes, probably. I mean, obviously it depends on the Haskell binary, right? But I'm confident. For example, when we did the EDSL, it was pretty bound to Haskell, right? I mean, Haskell is a good language for EDSLs, and that's why we chose it. But now I'm pretty sure that we can rewrite the tool in a different language, for example, C++, something that targets efficiency and speed. And now, of course, the final user will never notice that. And also the specification, the theory engineer, the one who has to be an expert in the underlying language, I think a different language will not be so harsh with them. I mean, in other words, we did it in Haskell because we came from an EDSL, but you can, I think from now on, it might be a good exercise to move to a different language like C++ and keep all these, all this architecture.
That will be more because you are consumers.
Sorry?
It will be more because your consumers are going to be people who have experienced more in C++ than in Haskell.
Probably, yeah.
Thank you very much.
Thank you.
Thanks very much.
Do I count? 5? Okay.
The next talk will be about checking concurrency coding rules. It will be done by Julio Marinho. Very much.
Yeah. Okay, so this is another talk on trace analysis and a practical application of logic programming to build a kind of embedded DSL. In this case, it's an application to a very practical and focused problem. We are teaching concurrency in a public university in Spain with a lot of students. And we have some coding assignments. And well, concurrency is hard sometimes. And there are many things that can be error prone. And our idea is that there must be some checking of the code submitted by the students. We must do as much as we can in order to reveal errors in their submissions, right? The alternative is just run some poor tests and so on. So we are going to show how we managed to obtain a practical but cheap solution by combining logic programming as a way of defining a specific language with some on-the-shelf tools that allow us to obtain execution traces from Java programs. The course is centered in Java programming, right? So we think that you can take some lessons in order to program similar systems for code analysis in other contexts. And this is available with an open license at our research group GitLab repository. And well, this is a work that elaborates on previous work, similar things by our group. On one hand, there is a particular approach to teaching concurrency based on formal specifications. We define the problem to be implemented around a state-based model. So it's a model-driven methodology. So you're based on the model in order to write the code and also in order to produce the tests and so on. This is one of the papers where this is defining and where we defend that this is useful for teaching concurrency. And also, we had some prior experience in a European project on defining coding rules for C and C++. In fact, we already defined a DSL in Prolog called CRISP for coding rules in Sugar Prolog, where we defined a lot of coding rules in use in the industry, like high integrity C++ or similar to MISRA C using Prolog. That was a project that stopped in purely structural rules. I mean, rules that had to do with the abstract syntax tree of the program, rather with the behavior of the program, which operations are done in which order. And in this particular application, we are focusing more on the behavioral patterns, that you do this before than this, and you don't do this unless this condition is met. So it's more about detecting faults in the code by a post-mortem analysis of the traces of the program. So in order to understand what is happening here, what we have here is this is the basic setting on about how we grade our student submissions, right? To make an idea, we receive around 200 submissions for every 2 students, right? We have around 400 students and 200 submissions. So first we give a problem statement in natural language, and we also provide a formal specification of process interaction. So it's basically a state-based model like TLA, not exactly the same syntax, but basically we formally specify an API of atomic linearizable operations and how they interact, right? And from that, the students are assumed to produce a Java class implementation using different techniques. Okay, so what the students receive is a test report that is obtained using property-based testing from the formal specification. This is done semi-automatically. We work a lot on property-based testing of stateful systems. So this is something which we have a lot of practice. So the unit tests are generated from the specification, and they take the code produced by the students, and these are reproducible chains of codes to the API, so that if some of the tests fails, the student knows that if he or she submits again, the sequence of codes to the API is going to be the same, right? So they're going to reproduce the same errors. And what we have added a couple of years ago is, beyond the tests, this behavioral analysis of the code. So basically, we add this event tracing facility that, along with some specific knowledge that is obtained from the formal specification and the coding rules written in Prolog, produce an additional coding style report or coding rule report that is mainly used for us in order to complement the test information, so as to detect the source of the errors. I think that this is one of the best lessons learned from this system, that these two informations are complementary. And this is something that you can apply also in industrial contexts. Okay, so this is the looks of a formal specification for interrupt process. It's very similar to TLA or VDM, if you're familiar with. And basically, for every operation in the API, this is the API. This is an idealized bank account example with operations for deposit transfers, balance, and also alerts on some low income or so. And we define the inputs, and all these operations have a special characteristic that they're all expected to behave with linear semantics. They should be linearizable, right, in the Hartley-Wing sense, right? So whatever implementation you do of this API must respect this linearizability restriction, and there are also requirements regarding liveness, deadlocks freeness and so on that must be respected in the subsequent Java implementation for this. So for every operation here, you're expected to have there's going to be a Java bank class, and there are going to be 4 methods here. So basically what you have in one of these operations like this is the pre is a standard precondition. It's something that if it's not met about the state of the system itself is a pronoun, is like this. It's a reference to the state of the system, which in this case is a map from account identifiers into the money you have in the account. And pre is a standard precondition, so if it fails when you call alert, then you should launch an exception. C-pre, or the concurrency precondition, is something that, if not met when calling the operation, should lock temporarily until a future state where the state meets the condition. And the postcondition in general is how the state of the system changes immediately after completing the operation. So it's a transactional semantics for the operations in the API, right? It's basically the idea. So in this case, alert doesn't change the state, but other operations like transfer, for instance, change the amount of money you have in the system. Okay, so that would be a reference operation for this. You are going to translate API methods into Java code, and you're going to implement this with some libraries. For instance, you may use a monitor library or a semaphore library or a message passing library, and these are some key operations that you have in the library. So in general, this is a method of analyzing how you are using some library in general. So that would be a reference implementation for the state. You may represent the state of the bank in this way, and that could be a reference or correct implementation for the transfer operation, right? In this case, the student could get a good grade, right? So it can get a bit tricky because you have to check in general preconditions and launch exceptions, or you have to block if the concurrency precondition does not hold, and that means using some blocking constructs in your library and so on. And you also have to unlock other threads. Maybe if you transfer money from one account to another, then you can unblock other threads that are waiting to retrieve money from another account and so on. So this code can get rather tricky in general. Okay, so what we have expressed in our coding rules DSL is a set of common errors that we have found in the submissions. So like you should only call enter once, because if you enter and leave the monitor several times in one of those operations, you lose atomicity, right? So you can have interference with other operations. That's quite obvious. Or for instance, you should only launch one signal per API operation, because the semantics of repeated signals can get very tricky, and reasoning about problems with many signals is complex, so we forbid that, and so on. And the same with the blocking operations like the awaits in monitors and so on. So in general, our experience on about what kind of errors do the students make has been condensed into a set of common error that we are going to represent in our DSL, right? Okay, so let's go with this first part, which is the collection of the traces from the execution of the submissions. We use for this a library called Byteman for Java, or Java Byteman, that allows us to specify rules on different events that happen in the execution of a Java program. This is one example of one Byteman rule that is used to launch events when the code of the students is calling some monitor operation, right? It's calling the enter operation in a monitor, right? So this is something that can be tailored to call some particular method by us that can output some Prolog fact. So in the end, when you apply this on a piece of Java code, then you're registering some events, and if the code finally calls a monitor enter, some Prolog fact with this information, where this is, for example, this is the identifier of the thread that launches this, what is called, and so on, and a lot of information. So the first thing we do is to gather information on the execution of the code using this Byteman library and create a very big event database stored in Prolog, right? Sorry. No. Okay, so in the end, this is a lot of pieces of trace information that we capture, and you have the detail of this in the paper. Okay, so after we collect this information in the trace, which is a Prolog fact database for some key events that happen in the execution of the submission, then we pass on to the trace analysis. So trace analysis have these three parts here, combines these three information. This is some specific knowledge about the properties of the expected properties of the actions in the formal specification. These are the coding rules that translate the good behavior that we expect from the code regarding execution properties, and this is the event trace log that get here. So the resource-specific knowledge is, well, it's not very interesting. It's about properties of about the arity of the operations, some specific details. For instance, there are some operations that do not block. For instance, deposit and balance do not block, so we mark this, and so on. Or whether they may throw an exception before actually executing or something like that. In the case of alert and balance, they don't change the state of the shared resource. So this is something that we need to know from the specification. And then we have the translation into Prolog of all the coding rules that we have. So the coding rules are Prolog predicates that reason about the event fact database that is gathered by Byteman as the different events of calls that happen in the program execution. So I have shown here a couple of them. So this is the negation of the rule that states that you should call enter only once in one of the operations of the API. So this is a Prolog rule that reads the different facts that are stored in the trace database, right? So in this case, we are using just existing facts, and in this case, we are just checking that the set of calls is of length 1, not of length 0, and not of length greater than 0. So in this case, this is quite simple, but we also have more complicated rules that, for instance, you should not signal until you haven't completed a transaction. You should signal other process when you have completed one transaction, you have changed, you have submitted all the changes in the transaction, and only in that case you should signal another thread, right? So in this case, we are using aggregation, we're using find all, we are traversing the event database, and then we're checking this, right? So we have a lot of coding rules. They are not trivial in general, but they do not get much larger than this. So if we, for instance, we detect that the students are doing some strange trick or something, it is very easy for us to define a new rule in Prolog and look for that behavioral pattern, that you're calling this before this or something like that. So for showing one example of the kind of errors that sometimes we discover and we don't expect them, some errors have to do with, for instance, dealing with preconditions in the wrong way. So for instance, we have two operations in the bank example that could launch an exception. One of them is alert. So if you're programming an alert on an account that doesn't exist, then you should launch an exception. So the precondition for alert is that the account identifier must be in the map from accounts to the money. So in general, if you're programming this with a monitor, you must first access the monitor in order to guarantee exclusive access to the table, then check the precondition, and if the precondition is not met, you should launch an exception, but only after releasing the monitor, because if you launch the exception without releasing the monitor, then you are forbidding the access from other threads. So typically, there are two kinds of errors associated with this. One is that you access the state of the bank without getting exclusive access. And in that case, this might get unnoticed by the unit tests, because the only possibility that you detect this is that there is a race condition, but some of the time you don't get a race condition. So that would be a wrong access that is not detected by the test suite, but the rule checker detects that. So if our coding rule checker detects that you're trying to access the state, but you didn't perform an enter on the monitor first in order to ask permission for exclusive access. So in that case, that would be the error that is produced. So we know that some submission is wrong, even if a unit test does not fail. And the other possibility is that they gain exclusive access to the monitor, they launch the exception, but they do not release the exclusive access. In that case, the unit tests are going to catch this error. But the problem is that the error is going to appear caused by the next thread that tries to access the monitor, because the monitor is taken, and it's going to provoke some kind of deadlock in the rest of the system. So we obtain a failure in the unit test, but the failure doesn't point the actual cause of the problem. So in this case, we obtain a message by the coding rule checker that, along with the unit test, tells us what is really going on that is causing the runtime error, right? So these are actual numbers from 209 submissions, where we program all these coding rules, and we find errors in, in average, in 35% of the submissions. 1/3 of the submissions had some kind of error, right? There were very strange errors or very common errors. Right? So when you're getting such a number of submissions, this is really helpful, right? For the students, the tests are useful because they tell them that something is going on. But for us, if we see that something is very common, it allows us to send some message or something, telling them, okay, you're doing something very, very wrong, right? So this is very practical. But I think it can be also practical if, for instance, you have a huge base, a huge programmer base in a company and you're doing a lot of submissions or commits. Okay, so basically the conclusions, the good conclusions is that this kind of behavioral rule checking is an effective way of complementing the information that unit tests provides, right? Because sometimes you don't know what is the actual cause of the error. This is very cheap. I mean, we didn't have to do a lot of things. I mean, Byteman produces just events that can be written onto a file. We use Prolog as a fact database, and then we define very declaratively the rules by traversing the event database using Prolog rules. This has been very, very simple, relatively simple. And we have incorporated this as an essential tool for grading the submissions. Limitations of this, one of the limitations of this is that this is behavioral. This doesn't work on the source code. So that means that it only detects wrong traces if those wrong traces are actually executed by the unit tests. So you need that the unit tests have a very good coverage in order to discover the problems in the source code, right? Fortunately, we work with unit tests that have been obtained automatically using property-based testing from the formal specification. So they have a very good coverage. We have improved this over the years. So in the end, if there's something wrong in the code, we usually discover this using this combined attack between the coding rules and the unit test, right? And as future work, there's always further possibilities of integrating this, especially with other tools that actually look at the source code and other static analyzers. Thank you. That's it.
Thanks for the presentation. At our school, every professor has different ways of coming up with some system to test 100, 200, 600 students' programming assignments. I'm of a philosophy that the test that I use to grade their code, the student should have access to my tests. Other professors have the idea, no, the student should not see the tests because then they can reverse engineer them. What's your opinion?
On both, in some sense. Okay. So it's true that students perform reverse engineering if they know the tests, right? But in this case, what we do, they don't know the tests, but they receive the sequences of calls. So if the test fails, we tell them, okay, there are, for instance, 10, let's say 10 unit tests that are 10 sequences of, let's say, 10 calls, right? So in the whole, you have like 100 calls to the API, right? So if the test is okay, you don't say anything. The test 1 passed, test 2 passed, test 3 failed. And test 3 failed in the 7th call. So the first call is, we call deposit, fetch, alert, blah, blah. And here, the behavior is not what we expected, because this alert should have awakened this thread, for instance. So we only give the essential information for them to know that something failed, but we don't reveal all the unit tests, and we change it. So we have several submissions, and we have a first stage and then a final stage. In the final stage, we learn from their mistakes, and we strengthen the tests.
How do the students test their own code?
No, in the case of concurrency, it's very hard for them to obtain a good coverage in the unit test. So we have our own submission system. We have a server running these tests all the time with virtualization and so on, because otherwise the bad submissions take all the CPU from the good submissions. And it has taken a lot of work from us, and that's it. The fact that the tests are deterministic is essential, because if they make a submission and they have only 2 errors, they need to know that in the next day, they're going to attack the same tests, right? So we don't change them very often, right? They are given a kind of mock-up system, right? So several threads that call the API, so they can change it while they're developing. And they do random calls and so on. So if they want to make their own tests, they can do that. So they only submit when they have randomly tested for several threads and so on, that more or less the behavior is sensible. But when they submit to our unit tester, the coverage, we cover corner cases because we have generated that with the PBT technique. And that's much harder. It usually reveals errors that they did not think about.
Thanks. So would it be possible to adapt this kind of tool to checking things that aren't necessarily runtime errors? And the reason I ask is because, at least in the past year or so, there's been a lot of interest in trying to detect whether code has been written by ChatGPT, for instance, as opposed to a student. Is that more of a static analysis sort of task?
I haven't thought of that. I mean, the origin of these coding rules and behaviors lies in embedded systems, from avionics, motors, and so on. So this comes from 20 or 30 years ago, and we didn't have this problem of code generated and reused. And we are now a project for dealing with that kind of code, but I haven't thought about whether this kind of behavioral analysis can reveal. Sometimes it depends on the application domain. Sometimes ChatGPT produces good code because it copies from the good sources, and other times the code obtained from ChatGPT is quite strange. And so I don't have a general answer for that.
Regarding one of the limitations that you mentioned, which is the generation of test cases. You mentioned that you use property-based testing for that, but that's based on random test case generation, I think. So have you considered to use a concolic tester, which typically gives a better coverage, or even a model checker if the number of states is finite, and so that you can check every possible execution up to partial order reduction?
Yes, it's always in our agenda. We didn't do that, but we want to do that because, as you know, I mean, one of the limitations of black box testing can be overcome with this kind of things. So yes, we plan to do that in the future.
There are many mature tools for
Yes.
testing, for instance, that you can use.
Yes, yes. It's just a matter of time. And this works because, I mean, if you want to catch errors, you do with that. I mean, probably for a more exhaustive industrial application, a better combination of techniques is needed.
1, 2.
Talk about an interesting question which I had never posed myself.
Thank you very much. So this talk is about, so can we get rid of predicates and backtracking in logic programming? And I'm trying to show you that it is possible, and maybe I convince you that it is also reasonable. And the good thing is we can have a better operational semantics, nicer programs, and close the gap between theory and practice. So first we start about theory. In logic programming, we have an ideal view, so that problem specifications are written with horn clauses, and we have SLD resolution, and we know by the completeness of SLD resolution, it is possible to compute all solutions to a given problem. However, there is also practice, and this is Prolog. Prolog is based on backtracking with a justification. 50 years ago, we had not so much memory, and this causes also a loss of completeness. What are the problems? So the main problem is we have to write everything in flat form. So this is the well-known append predicate. And if we want to append 3 lists, we have to flatten the nested call that we want to apply append to append. And we have to write it in this way. And this makes no problems, for instance, in some situations. So for instance, if we want to compute 3 lists such that a concatenation is the empty list, we get the solution. Okay, all 3 lists must be empty. But when we ask for more solution, we do not terminate. And even if we, for instance, here ask for an unsatisfiable goal, we might not terminate instead of getting the answer just no. So, and I want to show you that if you replace predicates by functions, you can do it better. So there is a thing which we have also heard this morning, function logic programming, where the idea is that the program is a set of functions defined by equations, and it does not only provide a compact notation, but you can also exploit the functional dependencies for better operational semantics. And I will show it you here with the case for curry. And the operational semantics of curry is based on demand-driven reduction of function calls, which is taken from functional programming, and non-deterministic rule application. So due to non-deterministic rule application, we have all the power of logic programming, but due to the demand-driven reduction of function calls, we can do better. And here is the same program as before, written in curry syntax, so basically it's Haskell syntax, where we can now concatenate 3 lists by just having a nested application. And the consequence is we can solve here this equation by asking for 3 lists such that the concatenation is the empty list. But we have also finite evaluation. So if we ask for more solution, and basically curry immediately computes all possible solutions, we have a finite evaluation. And for instance, for an unsatisfiable equation, we just get the information, no results. We have it also in finite manner. So I do not want to discuss details how it is obtained, but the question is, can we do it also systematically? Does it only work for this example? How does it work in general? And therefore, I worked on a systematic transformation method to transform pure logic programs into curry programs. And this is done in a tool. And there are also references for this. And I do not want to discuss the idea, but I only want to stress that you can translate any almost pure Prolog program, so without cuts and side effects and so on, into a curry program. And what are the advantages of this? One can show that we have a semantic equivalence. So that means all answers which are computed in Prolog can be also computed in the transform program. In the worst case, we have the same number of evaluation steps. We have no advantage. But this is only the worst case. In the more general cases, we have less evaluation steps. And this is due to the fact that some sub-expression might not demand it. And as we have seen before in the example on the previous slide, we can also reduce infinite search spaces to finite ones. So and this shows you also some benchmark, how does it perform in practice. So I tested here the SWI Prolog, Sixtus Prolog on different kind of benchmarks. The first three is list reversal, tuck, and Ackermann. So these are purely functional programs where we have no advantage of this transformation, because basically everything must be evaluated in them. But here we have the implementation kicks, which compiles query programs into Haskell programs. And you can see here from this number, due to the implementation strategy of the Glasgow Haskell compiler, programs run much faster. But then we have also a group of examples here where we have on the Prolog side an infinite search spaces, because we ask for infinitely many data structures. And in the query side, we have a really small search space. And then there is also another group here where we have a finite search space, but the search space reduction is interesting here, because the permutation sort means in the Prolog side, we have to compute all possible permutations, which is factorial to the length of the list. And due to the demand-driven explanation of the search space, we have here really reduction in the complexity of the problem. So therefore, we can learn one can get rid of predicates by functions, and we have no disadvantage of doing this. Now, how can we avoid backtracking? So in Prolog, the bad answer is we cannot do it, because backtracking is built in Prolog, as I said. The original motivation were limited hardware resources, and it is not today easy to change, because many non-logical features of Prolog rely on backtracking. So we have to use a completely new language. Fortunately, we can test it in Curry, whether it is possible, because Curry was developed as a declarative programming language, and therefore the search strategy is not fixed. Actually, there are different Curry systems or Curry compilers which have different strategies. For instance, the PAX system compiles into Prolog and therefore uses backtracking. But there is also the KIX2 system, which compiles into Haskell, which offers depth-first search, breadth-first search, iterative deepening, and more strategies. And then there is also recent implementation where Curry programs compiled into Go programs. And there is offered, you have depth-first search, breadth-first, and you have also a fair search strategy, which is implemented via coroutines, which means that the different alternatives are scheduled into different threads. So, and what is the advantage of fair search? That is really the only strategy which is operationally complete with respect to the theory. So for instance, this is an identity function. ID of n returns n, but on the left and right, we have a non-deterministic alternative, which is a just loop function, a deterministic looping function. And therefore, if we want to compute, for instance, identity applied to true, then the depth-first and breadth-first strategy just loops, because we have no choice here, because loop are just deterministically non-terminating function. But with the first search strategy, you get true as a result. So this also seems to be maybe only of theoretical interest. Maybe is the fair search strategy is very the implementation costs a lot of resources, and therefore I only want to show here on one slide a couple of benchmarks. And but the most interesting thing are the last three columns, because here we have evaluated the Curry-to-Go system, where all three strategies are available. And basically, you see there is no big difference between the first search strategy and the other strategy. So it's not costly to implement. And then there is also another interesting point here. For instance, these are the last two rows here, where we compute for a list where the list elements are costly to evaluate. These are prime numbers. And this is an insertion sort applied to this list, and this is a permutation sort. And usually would say insertion sort is a deterministic function, so it should behave much faster than the permutation sort. But here, for the first fair search strategy, it is different. Here, we need more time for the deterministic version than for the non-deterministic version. And the reason is that the non-deterministic version, then we schedule the non-determinism into different threads, And so this might have the effect that the evaluation are also scheduled to different threads, and therefore we can exploit parallelism for this. So therefore, the question was, can logic programming, not Prolog, but logic programming be liberated from predicates and backtracking? And the answer is yes, because you can replace functions by predicates by function. And as I've shown you, this gives only advantages, but no disadvantages. Because the transform program computes the same or more general answers. In the worst case, we have the same number of evaluation steps. And in the general cases, we have a reduction of the steps and also of the search space. And for particular classes of programs, we can also show that we have an optimal evaluation. That means we cannot do better. And the second thing was complete strategies, complete search strategy are not slow. And today we have enough memory and processors. They only need to require and want to work. And usually they have no work to do. And here we can give them work. Okay, the advantages, we can have also, if we use functions, we can also provide modern language concepts. So we can use functions, nested expressions, and so on, and not only this flat form. We can avoid incompleteness. That means we can close the theory and practice gap of logic programming. And it's also easier to teach logic programming. So I teach Prolog every year as in a mandatory class, and every year I have the problem to convince the students that Prolog is an interesting language because they often only look at the syntax and these limitations which they also see when they write the first programs and something does not terminate, which should give an answer. And then you have to explain them about the strategy and so on. And we can also avoid the non-declarative features. So, and I think this is the right way to keep the ideas of logic programming also in future programming systems. Okay, thank you very much.
This is a really stupid question, but based on the slides you had with the times, can we take PAX and instead of running it through Swipple or Sixtus, can we just compile it back to Curry and run it through the pair search?
Then what is the...
So PAX Curry programs compiles them to Prolog. Can we take that Prolog and run it? Oh, yeah. Okay. Shoot. Oh, well.
Logic language, you do not need cuts because you have functions. Right. And in Prolog, we use the cuts to simulate the functional behavior. Oh. Sorry.
Although I'm quite convinced of the ideas that you have mentioned, or you already know, I have worked with you in some of these topics. My personal opinion is that there are still, even if this is true and you get something that is more efficient, in my impression, there are some problems that can be more easily expressed in a language like Prolog than in a language like this, using functions and so on.
Also Prolog, because you can also just write Boolean function and then they are equivalent to predicates. But this is not a good idea because it's better to express, if you have functional dependencies, to express them in function. But you can just write, because this is in the paper where I've developed the transformation from Prolog into Curry, I called this a conservative transformation, just replacing Prolog predicates as Boolean function, and then you can see that SLD resolution is exactly the same as narrowing on Curry.
How do you represent a conjunction or a sequence of atoms in the body of a clause?
Conjunctions are just, because it's a Boolean function, you use the AND operator. It's just the standard AND. The conjunction, and therefore it is equivalent because the conjunction is also defined in such a way that first you have to check the left conjunct for true and false, and then go to the right. And this is also a strategy which you use in Prolog.
Fine, so.
Can think about it and give me other examples which you can think, which you can.
To replace, say, Prolog with such a language, or you consider that Prolog could be compiled using this approach?
I only wanted to show that basic query programs are always better. Now the idea is not that you take any Prolog program, because the problem is it was really hard to look at the examples which I've shown to you, because any realistic Prolog program using non-declarative features, side effects, and so on. And therefore, this should only show that you always can do better, but then you can also have to replace the side affecting things by better approaches. So for instance, replacing I/O but by monadic I/O and so on. So this is the idea. So the idea is not really to translate everything.
Particular example in mind now, but I remember that some problems that I could express in Prolog in a very compact and intuitive way, when I try to translate them to a functional notation, they become less natural and more complex. Some examples.
Where you can argue is that Prolog is dynamically typed, so you have not such a strict type system. But my answer is I'm doing programming in Prolog as well as in Curry, so I do not like to miss the type system, because all the errors which I get, type errors which I get from the Curry compiler, then I have to debug my Prolog programs long time for getting this. And so I can live with the restriction of a strong type system.
Another point is, for instance, there are recent approaches to add probabilities to Prolog. And that's quite natural in Prolog. In a functional syntax, not so obvious. So in Prolog, you can say, I have a fact. The probability of this fact is, I don't know. In notation, this is not so.
Probabilities, so you can also do it most of the thing you can do it also there. So, but
because, I mean, in the usual approaches to add probabilities to Prolog, you have several heads, each one with a different probability. So if you have a goal-driven inference mechanism, you have to choose one of them, the one that matches. You don't need to check all of them, only the one that matches. In a typical extension of a functional notation with probabilities, what you have is several right-hand sides. So in principle, you have to try all of them. So it's not exactly the same situation. I'm not saying one approach is better than the other, but I mean,
and all the extension which we know for Prolog or data log and so on, this is a different thing. But the advantage, for instance, of these extensions like data Prolog, these are also more declarative than Prolog, but they are more restricted because they are not. It's not a universal programming language as Prolog. Mm-hmm.
Any more questions? Can I ask a question myself? So I like Prolog quite a lot, and I've been using it for a very long time. And there's a difference in the way I act programming Prolog. So I work in Python. I don't work much with functional languages. And I have the feeling that when you program in a functional language, you think in terms of the solution to the problem, the development, the function that's being developed. Whereas in Prolog, I tend to program as a sub-problems, things that are going to be put together. You don't think so? From your point of view, the mentality, the mindset of programming Prolog should be the same as functional languages.
I do not see there any difference, because basically you have a direct mapping from Prolog to functional logic programming, and only if you really exploit functions then you get all the advantages. Yeah, yeah, but. Yeah, yeah. So sometimes it's also a matter of taste, of course. You can. It's always in programming languages. So. Mm.
It's exponential and they're taking a lot of space, a lot of time, whatever techniques you use.
Yeah, but the question is where so the exponential problem is I think it's gone with if you use fair search, that because then you just schedule the things and so and yeah. So today we have enough memory. So for me the main problem is if I try to teach to younger students. So and then immediately I start teaching. This is the idea of logic programming. And immediately they write the first program and they do not terminate, or they do not get solution because of the backtracking strategy. And I think this is really frustrating. And then these people are gone. So yeah, but just start teaching with tabling. So yeah, you can, of course. I mentioned also some time to time tabling and other things, which how you can improve it. But the first question is, so you say here you just do rule-based programming, and then they got no answer. But there is an answer. There must be an answer, and I think this is a problem.
Have you tried doing Marx's table? You said for 60. For 60, right?
I have not compared, basically due to the fact that we have not built in tabling into Cori, because it's a lot of effort to do it. You know.
Thanks very much.
Thank you.
Is on? Yeah. Oops. Okay. Okay, so this is work by Ivan Perez, working on NASA Ames, and Angel Aranz, which is one of the authors in my previous talk. So Angel couldn't be here, has a lot of paper working in Madrid right now. So he asked me to present this because this is a good place, as you have seen, to discuss the connection between logic programming and functional programming, right? Okay, so here we are. Sorry for the spoiler. Okay, so basically this is just another take on this topic on either embedding logic programming in Haskell or the other way around, right? So in this case, there's a different motivation because they're actually using Haskell for some projects at NASA. And well, they realized that for certain libraries, they would be interested in adding some deductive capabilities to the existing functional code, right? Which is good for us. So when Ivan approached us, we told them, okay, you have basically two possibilities. One is the interlanguage interfacing. So try to think about one interface between Haskell and Prolog and so on. Or the other possibility is use Cori, which is a wonderful programming language and is the future of functional and logic programming. But for whatever reason, they were not happy to change existing code. I mean, for instance, you can think that they're using a very specific Haskell environment and very specific Haskell libraries. So it's not that easy to introduce this connection between different languages. So they have decided to embed some part of logic programming inside Haskell. So they used, basically what they did was to apply some solution that worked for an existing Haskell library that they use to this problem. And this is called, this is a kind of problem transformation that is this extensible types library, and they have used this to extend existing algebra data types with variables. So there's a generic construction that adds symbolic atoms to existing data. So which is not a new idea. There have been semantics of functional logic problems that use this idea of extending algebraic data types with special atoms and so on. So basically, this is what they do. They use problem transformation. They have defined a combinator DSL for conjunction, aggregators, and so on. And in the end, they prove that more or less this Haskell library can do basic logic and constraint programming without exiting Haskell. So we don't know the actual implications of this. This is the work in progress, how to assign a semantics to some of the constructions. But it is nice, and we thought it would be a nice proposal for you to know how they did it. Okay, so this is an actual Haskell code with a logic programming query using their technique. So there you have an algebra data type for defining piano naturals, right? And that would be the definition, the standard Prolog definition of lesser or equal comparison operator in Prolog, more or less, with two clauses, right? So x is lesser or equal than y if x is 0, or if both are different to 0, and x is the successor of x1, y is the successor of y1, and x1 is lesser or equal than y1. Okay, that's very basic logic programming. So what they do is that they define a new Haskell function that goes from, not from naturals, but from terms of naturals and terms of naturals into logic programming goals, right? Not Booleans, but goals. And this is the actual definition of this using the embedded DSL, right? So it's, there are some sugar here, but it's more or less real. So you apply exist to a function that takes two things, and you have these two cases. So this is a disjunction combinator. Either x is 0, or x is the successor of x prime. This is a conjunction combinator. Y is the successor of y prime, and x prime is lesser or equal than y prime. So basically, you can read this Haskell code like you read Prolog code, and you can call this Haskell find all function, find all the x, that x is lesser or equal than 2, and you obtain this list. So more or less it works. In the technical report, there are more elaborated examples. There's even a Sudoku written with the library, and it works as expected. So how do they do this? Well, basically, they make this problem transformation that traverses type definitions and is very generic, and was presented in a previous work by Ivan on this design pattern. So you start with an algebraic data type, and you obtain something that's kind of a homomorphism, a type of homomorphism, where you apply a function below each functor, right? So from natural, you obtain nat f that expects some f. So you have 0f and successor f, capital F, and it's applied to f applied to natural f of f. So this is, from these, you obtain this new data definition. This is a generic construct that you can do for every type that you have. And this is important because they're specifically interested in logical programming with types. So they don't buy these flexible types motive for not using Haskell. They want the types from Haskell, but they want the didactic capabilities in hard crosses, right? So they are very happy that there are types here. So From this, we define the term construction. Well, term is a type constructor that for any type can be either a variable with a name or a compound of that type. So when you apply the transformation to a given type using term, you obtain, in this case, the terms of type NAT, which is term of NATF term. Okay, so this can seem a bit tricky, but it works. So in the end, there is a library that performs this at compile time by program transformation, and there is also some desugaring. So in the end, from the X variable in Prolog, you would obtain the NAT term term V of X, but you can desugar this, you can sugar this, so you don't have to write the V. So the V is erased, and the user just inputs the quote X and so on. So you can desugar things. So in the internal representation is this NAT term representation, but the user just writes the variables in quotes, so it's more readable, right? And there are some combinators for manipulating the goals. So succeed and fail are like the true and fail in Prolog. We have the disjunction combinator that we saw before, the conjunction combinator that takes two goals and returns another goal, another Prolog goal, and this equality and unification operator that takes two terms, two polymorphic terms, and return a goal, right? And with this, you can compose any logic program, right? We also have existential quantification. There's even a cut. Of course, I don't like cuts, but they have implemented a cut. It's not based on backtracking. I think it's based on collecting a frontier semantics, but they have implemented the cut. And some aggregator operators. So if you're interested in this, there are a couple of papers that I will reference in the next slide. So far, they have managed to implement several things. So for future work, I will be part of that future work because I have some experience with semantics. We don't know what this means in general because we don't know how the functional features in Haskell are going to affect some examples and so on. And the prototype is quite slow, as you can imagine, because there's no an abstract machine executing this code, but it's basically an interpreter, right? Of course, you can improve that with partial validators and so on, but this is in a very early stage, if you want. There are also some examples where they are starting to introduce solvers for constraint logic programming in a very early stage. So these are the two papers, if you're interested in the technique. This logic programming with extensible types, and the previous work on this design pattern of extensible types by program transformation. And that's it. Thank you.
So I noticed that you use sort of ground representation for terms, so you don't have actual variables. And then from when I work on partial evaluation, I remember that then implementing a unification was very, very expensive. So do you know if they have problems with this, scalability problems?
A well-optimized unification routine, yeah. So it's at the moment this is very inefficient, of course.
Variables, then perhaps it's not possible or goes against the idea of what you're doing.
So
have taken this path, right? But once that someone working in Ames research has taken this path, I think this is interesting to discover what are the limitations. Perhaps one of the conclusions is that it's mindless to, to follow this path. But maybe there's some workaround, and by using functional programming optimizations, you can get something that is surprisingly okay for some examples. We don't know. So this is very exploratory. So this is why I think it is okay to be in the hands of somebody with a lot of experience on functional programming optimization. This gets better, right? But it's crazy. It's a bit crazy, I think.
You mentioned the motivation was that they have also some Prolog code and do not write them new. So what is the idea if here they have a different syntax? It should be
No, the motivation is because they have code that is already written in Haskell and that has been tested a lot. And for instance, if they embark it on some probe, it's very tested and they want to keep only one runtime environment for one language. They're not going to embed a Prolog implementation.
Okay.
That kind of limitation. So it's a very extreme restriction. I mean, it's not like for general purpose, I prefer covering them. Okay, I can buy that, but they have a particular limitation because these libraries have been developed for 10 years or so, and they don't want to change anything.
But these are then the Haskell libraries, and then they just want to add some Prolog code.
They don't want the interfacing problem because they want to be sure that there's no mistake in translating a Haskell data type into a Prolog data type, this kind of thing. So they work with very limited execution environments.
So going back to that motivation question, and I mean, I think we're probably all in agreement of this is maybe not the way we would choose to do it. But do they know there's a query compiler that actually generates Haskell code? And if they want to interface with, they could like write their query code, have the generated Haskell code, and then interface with that. Okay. I'm just saying that is technically an avenue. I don't know like how much people want to interface with generated code, but it is technically an